Good morning, everyone. I'm Sharafat Kadimova from the Office for Outer Space Affairs and will be moderating this workshop via audio. I would like to thank you, everyone, for joining us today. And on behalf of the Office for Outer Space Affairs and the Center for Spatial Information Science at the University of Tokyo, we welcome you all to this workshop. This workshop is a continuation of a series of the 3 training courses which were held from 2018 through 2020. At this workshop, together with my colleague from the University of Tokyo, we aim to provide an overview of the use of low-cost Gnss receiver systems for high accuracy positioning and data processing. I'm sure this will be a useful session for all of you. Such occasions are crucial as we continue to work towards bringing the benefits of Gnss technology to everyone and everywhere. To begin the workshop, I would like to make a presentation on the work which is carried out by the International Committee on Global Navigation Satellite System, to which our office serving as an executive secretariat. And also through the ICG, we supported since, as I said, 2018, this series of the workshop. Let me just share my slides. Okay. So, as I said, our office is serving as the executive secretariat to the International Committee on GNSS. It was established in 2005 and it provides a mechanism for multilateral discussion and coordination on GNSS issues of concern. It encourages coordination among GNSS providers, promotes the introduction and utilization of GNSS services in developing countries. It assists also GNSS users with their development plans and applications, contributes to sustainable development of the world, and also assure that GNSS interoperability and compatibility among providers and users of GNSS, as well as enhance services and applications. The ICG membership consists of current and future core regional and augmentation system providers, which are China with the Beidou system, European Union with Galileo, the Russian Federation with GLONASS, the United States with GPS, India with the NAVIC system, Japan with CSIS, as well as Nigeria with NICOMSAT. The state members of the United Nations, which have an active program in implementing or promoting a wide range of GNSS services and applications, also members of ICG. And as of today, among those countries are Italy, Malaysia, United Arab Emirates, Australia, and New Zealand, which joined the ICG last year at the 14th meeting of ICG. There are 21 organizations, among which governmental, non-governmental, as well as the United Nations entities are as members of ICG, as associate members or as observers. ICG meets annually. As I said, last meeting was held in India in 2019. This year, the 15th meeting of ICG will be hosted by our office, and it will be held here in Vienna from 27 September to 1st October. The United Arab Emirates has expressed already interest to host the 16th meeting of ICD in Abu Dhabi in 2022. Within the ICD, the Providers Forum was established, and the members of the Providers Forum are only those which are current and future core regional augmentation system providers. The matters which are considered by the Providers Forum is open service information dissemination, open service performance, spectrum protection. The Providers Forum normally meet in conjunction with ICD annual meetings, or as there are needs to discuss any additional matters before the ICD annual meetings takes place. The ICD functions based on the terms of reference, and it has its work plan. The work plan of ICD carried out by its 4 working groups, which are listed here. It's the System Signals and Services, which is led by the United States and Russian Federation, and it's looking at the matters related to compatibility and spectrum protection, interoperability and service standards, system of system operations. The working group on enhancement of GNSS performance, new services and capabilities, which is led by India, China and European Space Agency, is looking at the future and novel integrity solutions, implementation of interoperable GNSS space service volume and its evolution, examination of performance of atmospheric models, and established dialogue with space, weather, and remote sensing communities. The working group on information dissemination capacity building, which is led by our office, focused on education and training programs, promoting GNSS for scientific exploration, including space weather and its effects on GNSS. The working group on reference frames, timing and applications, which is led by 3 international organizations as IAD, IDS and FID, focused on timing and reference station networks. Detailed information about the work which is carried by these 4 working groups you can find in this link below, and also all the reports which and then presentations which were made at the meetings of the working groups. A little bit more detailed information about each working group. So the working group S, which is System Signals and Services, the latest work of this working group is on compatibility and spectrum protection. So this subgroup continues campaign to promote protection of GNSS spectrum through education and outreach. And normally we organize a training or a workshop to introduce this, and all the information which has been done until today is on this link, where you will find all the related materials. Well, this subgroup continues to investigate methods of implementing also interference detection and mitigation capabilities through the permanent network-based solution and crowdsourcing techniques. The following working group, working group B, the latest work of this working group is about the space service volume. During this work, all the providers were involved and agreed on the information which is presented in the booklet called the Interoperable GNSS Space Service Volume, and also on few recommendations to continue development, support, and expansion of the multi-GNSS space service volume concept. Currently, this work and its potential augmentations will enable ambitious future missions and activities in the context of space exploration, going beyond low Earth orbit to the Moon, Mars, and other celestial bodies. The The brochure is available electronically on the website of our office, and here is a direct link to this booklet. Also, this working group currently is working on the second edition of this topic, and the publication will be issued later this year and will be also made available on our website. The following group is the working group D on reference frames, timing and applications. A few areas where were made a significant progress is the refinement of the alignment of GNSS reference frames to the International Terrestrial Reference Frame. Also, information on GNSS timing references and the intercomparison GNSS time offsets. Periodically, the templates on geodetic and timing references updated by all GNSS providers to reflect the changes. And those templates are available at our website. Here the link to all the resources of this working group, as well as in cooperation with the working group B and S, the discussions are carried out on interoperability on GNSS precise point positioning services. The working group C, which is on capacity building and information dissemination, which is led by our office in the framework of that working group, also carries out so-called program on GNSS applications. And as a part of this program, we organize every year regional workshops, training courses on the use and applications of GNSS in order to reinforce the exchange of information between countries and scale up their capacities in the regions for pursuing the application of GNSS solutions. As well as we are looking at the sustainability and modernization of GNSS continuously operating reference stations and geospatial infrastructure through capacity development, in order to provide information on the importance of planning and its link to the why, what, and how of developing long-term capability with respect to GNSS and geospatial infrastructure and related activities. Another topic which is considered by in framework of this program is space weather and GNSS. The main aim here is to describe the science of space weather and how to perform ionospheric studies, as well as research with GNSS data. In the framework of the regional workshops, which are organized every year, this year we are planning to organize the workshop on GNSS applications in cooperation with the government of Mongolia. The workshop is planned to be held in Ulaanbaatar in October. Detailed information will be available on the link which is provided below. The main objectives of this workshop will be to address an array of GNSS applications for socioeconomic benefits and to focus on initiating pilot projects and strengthening the networking of GNSS-related institutions in the region. Also, the special session in coordination with the Working Group S will be organized on the GNSS spectrum protection and interference detection and mitigation. In cooperation with the Working Group D, we will be having a session on regional and national reference frames and system and perspectives of regional cooperating mechanism. Also, as a part of the Working Group C work plan, so we are organizing, as I said, the series of the training courses on GNSS data processing, and today this is this session is a part of that series. It's the second part of the series. The first part was on GNSS data processing. This part is dedicated to for decision and policymakers. As I said, this is a series which is organized with the University of Tokyo of Japan, and our aim is to provide knowledge about the use of low-cost Gnss receiver systems and Android devices for high accuracy positioning, survey methods, and data processing for a high accuracy in real-time or post-processing modes. We're also planning to prepare a handbook on high accuracy Gnss data processing, which will summarize the data processing techniques, error analysis, and various concepts related to the setup of base stations, rover units, and software. This is planned to be published next year, by the end of the next year. So all the detailed information and the materials presented in the series of these workshops since 2018 can be found at the link provided at the below on this slide. So, and as I said, also we are organizing a series of the training courses on and workshops on space weather and GNSS. This activity is carried out in cooperation with the Institute for Scientific Research at Boston College of the United States and the Abdus Salam International Center for Theoretical Physics, which is based in Trieste in Italy. This year, we are planning to have the workshop on GNSS and space weather. It will be held in October and hosted by our regional center, which is based in Rabat in Morocco. This workshop, we're planning to introduce the ionospheric physics and the science of space weather, which includes also basic knowledge of GNSS technology and its applications. The main focus will be on space weather research using GNSS data. Detailed information about the workshop will be given on our website. Also, we organized last year online version of this workshop, and the materials of that workshop, if you are interested, is available on the link below. Well, as I said, there are regional centers for space science and technology education, which are affiliated to the United Nations through agreement with our office. Those centers are based in Africa, in Morocco and Nigeria for French-speaking and English-speaking African countries. There are 2 centers also in China and India for the Asia and the Pacific region, and the 2 campuses in Brazil and Mexico for the Latin America and the Caribbean, and the center in Jordan for Western Asia. These centers carry out 9-month postgraduate courses on remote sensing, satellite communications, and also on GNSS. You see here the cover page of the GNSS education curriculum, which is available in 4 languages. It's English, French, Spanish, and Arabic, and can be downloaded from our website if you are interested to use the outline of this education curriculum in your institutions. Well, with that, I conclude my presentation, and in conclusion, the activities and opportunities that we provide through the IZAG result in the development and growth of capacities that will enable each country to enhance its knowledge, understanding, and practical experience in those aspects of GNSS technology that have the potential for a greater impact on its economic and social development, including the preservation of its environment. As I said, all the information related on ICD activities is available on our website, the top line, it's the link to this website. And below the link is to all the publications which have been issued by ICED until today. You can find at this link. With that, I would like to conclude my presentation, and will in a minute give the floor to my colleague Gnss Manandar from the University of Tokyo. I would also like to tell you that all the topics or presentations which will be made today, mostly by the representatives of the Tokyo University, are recorded, and it will be edited and will be posted on the UNUSA's YouTube channel. And once it is done, we will let you know and provide you the link. Also, the materials of the previous session of this workshop are available, as I said, on our website, and you can also download those presentations. So with that, I conclude my presentation, and I'm very pleased to give the floor to my colleague Gnss Manandar from the University of Tokyo. Gnss, the floor is yours, please.
Yeah. Thank you, Shafa. Okay, so let me just set up my slides.
Okay, while Gnss is setting up his slides, if you have any questions for him, please write down them in the chat, and I think after each part of his presentation, he will be answering your questions. Thank you.
Yeah. Just a minute. Okay, thank you. So let me share my screen, and where is it? Okay. Okay, I suppose you can see my screen now. So this workshop or this training, I don't know whether I think we call it workshop. So this is actually the second one. We had a training, more detailed training last week. So I suppose that some of you also joined that training. And this is just for 1 day or 4 hours. Today is basically for policy and decision makers, because the reason I put this title, it has some meaning. We used to conduct a training with ICZ for the last 3 years continuously in the university in Thailand, actually. So every year in January, but this year we could not do it due to COVID. And when we did the survey with the participants of that training, so we got some information that, or feedback that, when they go back to use the system or the technology or the knowledge they gain from the training in their office or organization, so sometimes there's a problem because of to explain what is GNSS, okay, in the organization, or because when you go back after the training, so they do need some support in the organization or the institute. And at the policy or decision-making level, sometimes this information is not clear or not available because GNSS itself is a bit new topics for many of us. And it's now getting very popular in the last 5 years or 10 years after so many countries coming up to provide a service. So we decided to have at least some introductory level of this workshop or training, even at the higher level, so that the participants can benefit from that. But this is at very introductory level, just to give you some keywords, so we don't go much details. But in this workshop as well, so actually the objective itself is I have put some objectives here. So we try to give you a very overview of the technology and application of GNSS, and we'll show you some applications, what type of applications are there, and what are new applications coming up. Like I put here early warning system, which is not related with the position data or surveying and mapping. It's completely different services or different types of application. And this probably you know very much, illegal fishing or vessel monitoring in some of your countries, those countries that have a sea, and dynamic road pricing or traffic congestion, and all these are coming up, and we are working on that. So these three things actually, those applications where I myself is directly involved and doing coordination with other countries, basically in Asia. But I think this problem is very much similar to other countries as well, in like Latin America or the Africa and other parts of the world. And also, in order to do this type of application, you probably need a very low cost system to do like a training, capacity development, education and training, and collecting the data or doing some pilot project, because before going to the full-fledged project, you probably need to do some pilot project or do the proof of concept, POC, to see whether the system actually works for your system or not. Because technically, or when we look at this type of presentations, it's very fascinating and seems very fancy. But when you really try to implement the project, sometimes, many times, it doesn't work. It fails because of many other things, not because of the technology, but because of many other things, like you don't have enough resources, human resources, you don't have the know-how to collect the data, you don't have a know-how to process the data, lagging of the software, hardware, and if you have to pay $10,000 for one receiver, that may be too difficult as well. So this is where we're working now to have a very low-cost system. So I will give you this little bit in the third part of my presentation after the break, rather in detail. This is very important. And these are some issues that you have to be careful when you develop the system, because due to this issue, sometimes it may not work for your purpose. So you need to be careful how to avoid this type of problems. So some problems probably you cannot, like this one, you have no way to do it, but this issue is not big at the moment, the spoofing issue, but it may be in the coming 5 or 10 years. So once you develop a system, so make sure that these type of things may come in future, and your system is this proof of, I mean, they can withstand this type of issues that you may encounter in future. And then finally, this is a very important topic, and also many people are not much aware of this. And when you want to buy, okay, now you decide you want to do some project and you want to buy a receiver, and you call a company, okay, I want to buy a receiver, so please give me the specification and the price. So they will send you the technical document, and they send you a price. So the price may be from $1,000 to maybe $10,000, $20,000, and $30,000. And you really don't know which one is good for you. So that may be a very critical thing and very difficult sometimes in the purchase or in the procurement department of the company or in the government. So again, the process is very lengthy and they really need to make a good technical specification and so on. But to do all these within these 2 hours is impossible. But I will just highlight on the keywords and some points that has to be considered. So your system should not be over-spec, otherwise it will be too expensive and too complicated to operate and manage. So these are the objectives of this 4 hours or 3 hours lecture today or presentation that I will be doing most of the time. And during this, so we'd like to have a more free discussion as well. So please send in the chat, or if you want to speak, so please put your speaker on and you can even talk. So we'll try the best to do this talk as well today. So these are the objectives, and just looking at, so I was just looking at the applicants for this training. So actually there were so many applicants, but today I didn't see so many people. But if you look at the country list, so they are around the world. And due to this time zone, for some people, it's not possible to attend, because I got some email from Latin America in the last training, and they were attending and said, oh, I'm attending your training, it was very good, but it's 3 a.m. in the morning here. So because Japan, I'm in Tokyo, so Tokyo and Argentina just exactly 12 hours, so it's 3 a.m. now. But people are still attending this, and some there are quite few participants from Africa as well last time, so completely different time zone. and it's very difficult to manage the time zone that is comfortable for everybody, like a USA or Argentina and this region. So it's a little bit difficult for them. But anyway, we try our best. And this presentation document will be available offline later from the ICG homepage. And after the training last week, so I also got some emails from the participants requesting for software and some other additional informations and collaborations and so on. Okay, so these are the age groups. So I just look at the age groups so who are attending here. So it's very interesting to find out that we rather have this type of middle career already, 30, 40, and also some of us are quite senior. So I myself belong to this group. So we have a very wide variety of the participants, and when I look at the application list, also I found that so I think many of you already know what is GNSS. So we have a very beginners, and also we have experts here. We have people from the space agencies who are designing the satellite itself. So very diverse types of participants, and it's rather difficult to meet all expectation of everybody in this training. So, but this will be a very basic one. Yeah, and this is one very important disclaimer from my side today, because we have a technical specification, and I'm actually relating to the technical spec from some of the manufacturers. So there are some companies name I have to take, because we need to look at the technical spec of these companies and see the real spec. We just can't work on some values. So we really need to understand how they interpret the values, how they write the same thing in a different way. So when they say accuracy, what do they mean? What does it mean by the accuracy? Okay, they say 10 centimeter accuracy, but how do you interpret this 10 centimeter? That we'll talk today. And so, but we put some names. We have a company names here, but it doesn't mean that we are directly or indirectly preferring or we are recommending those companies. So don't take it otherwise. We have nothing to do, but we need to refer some companies because this is some technical real discussion we are going to do today. So it's up to you if you are interested. So you can look at them, you can contact them and see what they say and what they do. Okay. So this is one thing we have to note before I start my presentation. So now I'll go to my actual presentation. So my first part will be this one. So I have 4 or 5 presentations. So one is the technology and applications. There will be 2 presentations here. And then we have applications and low-cost receiver and this security issues. So a few slides here, and then finally we do this one. And I tried to cover this within this 3.5 hours. But depending upon this, I may not go to very detailed in this one because many of you already know this, probably know this, or please refer my handout after the training. You can get lots of references here. I put the reference homepage address and material address and so on. Also, just before Shafa mentioned that she mentioned already some references of the documents in the ICG homepage. So please refer those references, and there are lots of materials available, but you need to know which one is where. So that's what I'm going to do. But I'll provide the basic information to those who are new on this. So basically, we have different types of navigation types. So maybe this is a landmark based. So you navigate yourself based on some monuments. OK, I'm going to this park or I'm going to a zoo. So that's a type of a landmark based navigation. And this is very common in the marine. So celestial base, stars, moon. So you look at the location of the star and moons, but this is not in the past. It's OK, but now we don't use it. And this is very common or popular in the sensor-based navigation. So we use this even today, like we call it a dead reckoning, means you don't know the start point, the absolute coordinate you don't know in terms of the values. So we just say I'm starting from this point, like the aircraft, they know they fly from this airport. Okay. And from there, they can compute their direction and the speed and the distance, the way they travel, how much they have traveled. That's a sort of a dead reckoning, and it is done by using this gyro and accelerometers and compass and different types of sensors in the aircraft. And it is same thing in the marine, in the vessel or ships. Okay, they have different types of sensors to tell you the heading and the distance that you cover. But you have to know the initial reference point. Okay. But the problem of this type of systems is it's a bit complicated, and the errors, it accumulates very quickly. So we have a drift error, is the error that's related with respect to time. As the time pass by, the errors accumulate, and many types of errors, they are not proportional to time. So it's very, how to say, it's not uniform. Okay, so it doesn't change uniformly. It's very random or very non-uniform variation. So it's very difficult to predict or remove the error unless you have some reference data. But if you buy very expensive these type of gyros and accelerometers like in the aircraft, so they have a very, very small error even after flying for 24 hours. It doesn't change a lot. So, but it's too expensive. Then we have this radio-based navigation system. I don't think this exists anymore. Maybe just 1 or 2 countries in the world, this LoRaWAN may be working, but it's not popular. Technically, it's good, with even though it's low accuracy, but I think it's a little bit obsolete. And this is what we are talking, the GNSS. This is based on the satellite. So we use a satellite to send the radio signals. And Transit was the first satellite to do this type of tests. I mean, transmit the signal, but it's no more operational. Now we have GPS, GLONASS, Galileo, QGIS, Beidou, and IRNSS. So name has been changed to NAVIC. I did not change here, but this new name is NAVIC. And also the Beidou has an old name, Compass. Now it's Beidou. I think the official name is BDS. But anyway, so these are all the satellite-based navigation system, and this is the system that is now global and very reliable and very accurate, going to maybe centimeter level of accuracy. So this is the one we use. Okay. And when we say GNSS, so many people get confused with GNSS. They think, some people think that GNSS is a separate system like a GPS, but it is not. So when we say GNSS, so this is just a name collectively given to all these type of satellite systems like a GPS or GLONASS, Galileo, and so on. So in the past, we had only GPS and GLONASS, only 2 systems from USA and Russia. So we call them GPS or GLONASS, but now we have so many systems coming up from different countries. And collectively now we are saying GNSS. So when we say GNSS receiver, means that receiver is capable of getting signal from more than one system. Okay, so that receiver may have a capability to receive or may not have the capability to receive from all the satellites. But the architecture itself has a capability, but sometimes the receiver is controlled by the license or the cost. Like if you pay more, you get the capability to receive all the signals. If you don't pay for all the license, they will provide you probably only GPS or GPS and GLONASS and so on. But anyway, GNSS means all these combined system. And this is another thing that you will hear, SBUS, that's a satellite-based augmentation system, because this SBUS, the purpose of this SBUS is to provide some correction data for higher accuracy and integrity. For example, in the aircraft, ICAO regulation. So it has some requirement for GPS services. So to make sure that the GPS signal the receiver is getting is good enough. It can be reliable position data. So the receiver is always looking at the position accuracy and to make sure that this position is good enough for the requirement of the aircraft, and to ensure this type of quality or the service and availability and integrity. So additional data like orbit error, clock error, some other ionospheric correction data, they are transmitted from a different satellite, which is not the GPS or GLONASS. Okay, so this is what we call the augmentation system. So many service providers like USA and others, they have other satellite. Basically, these are the communication satellites, a stationary satellite, and they have a different name called WAS in USA, MSAS in Japan, Gnss in Europe, and Gagan in India, STCM in Russia, and Nigeria, I think from this year, from last year. So they started, not the last year, maybe quite a few years back, they started Nigeria SAT, Nigeria SBAS as well. So they have this service, and I think now this is continuously broadcasting the signal now. We can see this Nigeria SBAS satellite in some countries in Asia. If you look at the PR number, I think it's a 147. And also Korea is developing their own SBAS system, and in future they will also include a navigation system like a GPS type of system. And then also we have Australia and New Zealand coming up for their own SBAS system. So we are getting so many signals. So when you buy a receiver, you will see this type of keywords printed in the technical specification data. So this is what we'll talk about later. And let me show you some of these slides. So this is how it works, the GPS or GNSS system. So there's a satellite, and this satellite is sending some radio signal. So I'm showing here in terms of the pulse, but it's not the pulse, it's actually pulse, this type of PR and code, the pulses combined with the carrier and navigation data. So it looks like a very noisy type of signal. So I have another reason to show this type of a pulse to explain code phase and carrier phase and so on. But anyway, it broadcasts or transmits the signal at the satellite, and the receiver receives this signal, and when it receives, it computes the time to travel from satellite to the receiver. And by computing this travel time, so it can compute the distance. So if you can compute the distance, then you can calculate the position data. So basically, it's measuring the time of arrival from satellite to the receiver. And this is what's going on inside the receiver. So looking at this signal and computing the time of arrival here, and then computing the distance to the satellite. And then if you see multiple of satellites, then this will compute the position data for you. Yeah. So this is how it works. For example, if we have 4 satellites, so they all sending the signal, and then you get the 4 distances. The receiver calculates the 4 distances. This is what we call the pseudo range, or the distance between the satellite and the receiver. So in the data output, you will see the pseudo range data or carrier phase data, so on. So these are basically the distance between the satellite and the receiver. And if you have 4 such distances, then you can calculate the position data. Okay. So this is the distance between the satellite and the receiver. This is your receiver position data. This is the satellite position data. Okay. So we can compute the receiver position if we know the distance and the satellite's position. But we don't know the distance directly, so first we have to compute this distance, and then we'll compute the receiver's position data. In order to do that, this x0, which is the satellite position data, has to be known. But this satellite doesn't send its position data directly, because this satellite is moving on orbit, so it's always moving, changing its position data. So instead of sending x0, y0, and z0, the position of the satellite, this is the position of the receiver. So this is the position of the satellite xk. So we compute x0, y0, z0. This is the position of the receiver, and this is the position of the satellite xk, yk, zk. And this sk is not sent directly from the satellite, but the orbit data we call the ephemeris data, that is broadcasted from here continuously to the receiver. So the receiver getting the ephemeris data and the time data. So orbit data and time data are sent from here continuously, and using that orbit and time data, we can compute the position of this satellite at that particular time. So you have xk by using the ephemeris data and time data. You have the distance by measuring the time of travel from satellite to the receiver, then you compute x0, y0, z0. But this equation, as you see, here's a square and the square root, so it's a bit complex. So you do all this normalization and least square mathematics and all, and then you will get it. And also this B is some error, including the clock error here, because we use a very cheap clock inside the receiver to make a very low cost systems. Satellites have atomic clock. It's very accurate, but very expensive. We cannot have such accurate clock here. So we just use a very cheap clock, and that has error. So that error has to be removed. So this is also unknown. So there are 4 unknowns. So 1, 2, xk, yk, zk, and this B. That's the reason we need at least 4 satellites to solve this mathematics problem. Okay, so if you have 4 satellites, you can get your x0, y0, z0 and time. Okay? But we prefer to have more to have a better accuracy and a better availability and so on. So this is the fundamental thing how it works. Okay, I suppose that some of you already know it, so maybe not so interesting for some of the participants, but those who are new or not very familiar. So this is the basic thing. So please remember this, and based on this, we will be talking about the data type, errors, pseudo range. So we talk about the pseudo range, that's the distance between the satellite to the receiver. We talk about the carrier phase, that's the number of cycles the carrier signal coming from the satellite to the receiver, and counting those cycles, how many cycles are coming here. So all these will be used by the receiver to compute the position data. And this is the architecture of any type of Gnss system, whether it's a GPS, GLONASS, Galileo, QZ, Beidou, it's very much similar. So you need a satellite component, and then you need a control system here to see whether the satellites are moving along the orbit correctly, because they drift a little bit with respect to time, the orbit drift, and that causes the positioning accuracy. So this has to be monitored continuously. Satellite will be getting older. They have a limited lifespan, so they have to be monitored and see whether it's functioning well or not. So this type of control station is necessary. And here's the user. So these are the Gnss receivers that you have in different systems, car or your mobile phone. You have very small Gnss chipset inside your mobile phone or GPS chipset, and many aviation, marine, all the systems where you require the position data or time data. It's 2 things. So position, wherever you need position data, wherever you need time data, GPS is now being used, or GNSS. Now I move towards the systems to give you a little bit of information. So this is just a quick overview. So I don't go to all the details, this background and history and all, what type of signals and all. And this document I updated on 20 September 11. But please look at the latest material in the this ICZ UNOSA homepage. Okay. So they have the latest information. Also this page, the gps.gov, is the official website. So if you need a detailed this type of information, please go to the official site of each of the service provider, GPS, GLONASS, Galileo. All these service providers, they have official homepage. And also there are all these meetings, discussions, technical things, and workshops. So also ICZ has all these meetings, so you can find the references here. Please check these websites for details. Okay, I'll just give you the reference, and this I will talk a little bit, because when we talk about the technical specifications, you will see this type of values. Band L1, L2, L5. So when you go to a GPS, the company to buy, they will ask you, do you want L1 or L2, or L1 or L1 and L2? Do you want single frequency or dual frequency or triple frequency receiver? So these are the questions they will ask you, and based on that, price may be different. And you need to know what is L1, what is L2, what is L5, and why you need L1, L2, L5. Why not only L1? Okay, so these are the things we'll see in today's discussion. But anyway, so for GPS we have L1, L2, L5. For other receiver we also have L6, like a QZ, and like a Beidou they have B1, B2, B3, And GLONASS, they also have L1, L2, and L3 now, new signal. So different frequencies coming up. So these are bands, and they refer to this frequency. And within this frequency band, they have different types of signals. Like for GPS, it's a CA, C, and these are PY is a military. We cannot use these. Are for civilian. We can use this, but we cannot use this one. Okay. And then we have all these type of different types of signals: CM, CL, PY, and L5, I and Q channel or signal we have. So all these signals have a different purpose to use. And based on these signals, the cost of the receiver and the complexity of the receiver, it gets higher and higher. So you pay more if you need all, but you have to make a decision whether you really need all of these or whether you just need L1, L2 to frequency or signal, or whether you are okay with L1 and L5. So which one is better? That we have to know. And for GLONASS, so again, I don't have this latest one. I didn't update because these documents keep on changing. So I'm just giving you the reference here. Okay, and also you can see this is the same thing. So okay, so please check here for the latest one for GLONASS. And for Galileo, and this is the reference. Also, you see their plan. You will see this type of a chart in their homepage. But for Galileo, last week we had a presentation from Galileo from Europe, and he provided this handout. So please refer the last week information about the Galileo. You can see the reference here. So please download this. You will see some new information and also many other materials he has provided here in his this document. So there you will see lots of latest documents references here. So if you want to get more technical or more system related information, all are available here. And for Beidou, so please check again for this one, the latest. I think it's available here. I'm not sure whether there are other updates at the ICG after this. Probably not, because due to COVID, we did not have this meeting so far. Maybe it will be done online. And for QG also, please see this presentation last week. So we have the latest information here, and there are some new information as well related with the application, especially about the early warning system. So please check, and some other QGIS activities that's going on or around in Asian countries. So please check. So I would like just to tell you that the QGIS has a little bit different type of orbit, and this orbit is designed in such a way that you will see now we have 4 satellites, so you will see at least 2 satellites most of the time above your head. But this is a bit older one, so you can see the new one. So you will see now 2 satellites at a very high elevation. That means even if you go to a very high rise, this type of a skyscraper, the area in the middle of Tokyo, you still see a few satellites above your head. And by using those satellites, you can have a good position data. Because as you know, for good position data, you need a line of sight between your receiver and the satellite. But when they are at very tall buildings, so you cannot get it. And if you want to do like a car on the road, like a transport related application, so it's very, very difficult. So that's the reason QGIS orbit was designed like this, so that you will see some satellites above your head, even if they are tall buildings, so you will still get signals from QGIS, and then you will see some other GPS satellites, and then you combine QGIS and GPS and other satellite systems so that you can compute the position data. And GPS and QGIS signals are very much compatible. They have a same or similar signal design aspects. So the same receiver with some simple modification, it can be used also for QGIS. And this is for the NAVIC, the Indian satellite system. And this is also the slide from their presentation last week. So please go to this document. So you will see this slide. There were actually 4 or 5 presentations last week, so you will see all these presentations to this reference. Please check this. But the Navic has only 2 signal, L5 and S-band. So you see L5 and S-band. It's not like other GPS or other signals, other satellite systems. So this one, now I will show you this one, multi-GNSS signal. Now, if we summarize all the visible satellites and the systems, it will be like this. So we have L1 in this frequency, so many signals. This may not be updated as well. It's rather old as well. You can find the new ones in the internet or the ICG website or other reference materials. And here we have L5. But what I want to highlight or focus here is, now if you look at this chart, you see so many signals in L1 band. And also you see so many signals in L5. So, but you see fewer signals here, okay? For example, now, if you are going to buy a receiver, I recommend to buy at least L1 and L5 compatible receiver. So this will protect your investment in the receiver hardware purchase. But other receivers, other signals, it may be added later, or you may buy a separate license to use this. But if you look at this, so since these 2 signals are too crowded, the receiver manufacturers are designing a receiver, the new receivers, so that they can implement L1 and L5 together. Okay? But because they see most of the users will be here, L1 and L5, and L1 is already used for surveying and mapping in the civilian very heavily. L5 is basically designed for aviation and marine type of application, and also for the survey civilian. And also L5 is designed a little bit stronger signal compared to L1 to provide you better positioning accuracy. So in that sense, the combination of L1 and L5 will solve most of the problem. But currently, for RTK and all, so many models or the softwares like RTK processing software, PPP processing software, they are basically based on L1 and L2 signals, because these signals were existing from the past many years. When GPS started, it was only L1 and L2. So many algorithms and softwares and products were developed based on L1 and L2. So they are very much stable and quite good. So depending on your application, if it is for surveying and mapping, I think L1, L2 is better. But if you are doing something like IoT or like GIS and making a system for that, probably L1, L5 will be more suitable in terms of the cost and the future signal compatibility with the low-cost systems. And if you are going to use a mobile phone, the GNSS inside the mobile phone chipsets, the mobile phone manufacturers, they are focusing more on the L1 and L5. They are not focusing on L1 and L2 because they see lots of signal in L5. So if they make L5, they can accommodate all the service providers except GLONASS. Okay, you see here, but the GLONASS you have here in the L1, so it's okay. So you have L1, and then you have everything in the L5, all the service provider, including the Navi. Okay. So this is one guideline that we need to look at the signals, which one you should purchase and why. So this benefit of multi-GNSS, so once you have so many satellites and so many signals here, you see so many signals and so many satellite systems, so you can do a lot. So you have lots of choices now. You can have a very high accuracy services, and your system becomes more robust. If one system is not working, you have a choice to use another one. If, for example, if you have GLONASS is not working well in your area, so you have a choice to use the Galileo, or you have a choice to use the Beidou. If Beidou is not available, you have a choice to use another one. If QGIS is not visible, you can use another one. So you don't have to depend only in one system. Now you have so many choices, so many other things. And when we have so many satellites visible at the same time, so this type of some scientific research or the applications, they get a lot of benefit because, for example, in the past we have this type of soil moisture, wind velocity, and all these type of very scientific, highly scientific applications. So we have only maybe 10 or 12 satellites to measure the data. Now we can measure this data from maybe 40 or 50 satellites at the same time in real time. So it's becoming so much of data coming from different angle, different elevation, different azimuth, and so on. So you get the data coming from different angle, different directions and all. And that gives you lots of informations which were actually not possible in the past. Okay. And these are just some examples of how many satellites you see. These are current data recently in September 20. So these are our stations outside of Japan. So we have several stations that we established from our university. These are the Trimble NET-R9 receivers, very high-end survey-grade receiver. So we have a station in Jakarta, Bangkok, Manila, Tokyo, of course, Vietnam and Malaysia. Also, we have in Singapore, Myanmar, Laos, and some other countries, but I didn't put all here. But anyway, so this is, you see so many satellites. But in some stations, we don't have a license for all the signals, like this one, we don't have a Beidou. So you don't see the Beidou, and also this one, we don't have Beidou. But here we have Beidou, so all the signals, okay. So it's quite crowded now, you see. And if we look at the 24 hours data, so again, these are our station data in Tokyo, Jakarta, and this is in Mozambique. So we have a station in Mozambique as well, also in Rwanda. So you look at the data, because this is in the northern hemisphere. This is near the equator, and this is in the southern hemisphere, the Mozambique, the country. Okay. So in the northern hemisphere, we don't see GPS in this northern part. It's near the equator, so we don't see a little bit here in the north and south. Okay. So if you go to southern hemisphere, then due to the orbit design of the satellite, so you don't see here. Okay. So this is how GPS data looks like. But nevertheless, how they are visible, the accuracy, or if it is a good receiver, so when you buy this very high-end receiver, you have to look this type of data. We call the multipath data. This is not actually the reflection, so we can compute some of these parameters of the receiver using the raw data. There are software tools to do that. You should look at this multipath data, and for a good receiver, this multipath data should not exceed more than ±1 meter, okay, without doing any correction. So you just log the 24 hours data, you plot it, and you get this type of observation. Okay. So this is how it looks like for a good receiver. But also it depends on the antenna, not only the receiver, but your antenna has to be good as well. And where is your antenna located? If it is very high, that means either your receiver is not good, or your antenna is not good, or the location where you put the antenna is not good. Probably, if that's a survey-grade receiver, probably the problem is with either antenna or the location where you put the antenna. So you put the antenna where you have other obstructing objects like tall buildings or many trees, so they affect the signal sometimes, and these values goes up for some time. Okay. If it goes up for all the time, 24 hours, then it's probably the problem with the receiver or antenna. But for example, if it goes up like a certain time interval for some satellite, then it's a multipath, some obstructing objects nearby your antenna. So that's not a good location to put your course station. So you have to look at the raw data, how it looks like. So just don't look at the position accuracy data. It doesn't tell you much because that's just the average data. So if you take average of this, you get a very small value. But if you look at the nature, the points, how they are distributed, then you see this type of the distribution of the errors. So, and this tells you the story whether your data is good enough to do the very high accuracy measurement or not. And this type of receivers are used to compute the accuracy of maybe 1 centimeter or 2 centimeter. So if you want to compute the accuracy of 1 and 2 centimeter, it must be a very, very good receiver, good antenna, and good location. Here, if you look at the individual observation, so the diversity is plus or minus 1 meter. So how do you get 1 or 2 centimeter from this data? So this is possible in the data processing technique. So this is what the data processors or the experts, they look at this, or this is what they do. Okay, now let me finish this one, then we can take a few minutes of break before we go to the application. So the next, so let me tell you a little bit about the data formats, the 3 things, NMA, RINEX, and RTCM. So these 3 things you hear many times. Some of you, if you are already working on this, so probably it's nothing new for you. But those who are new, if somebody is here today, so I will just let them know that you will see this NMA sentence or NMA output all the time. This NMA includes the position output data from the receiver. So in case of GPS, so maybe it's a GPS position data, velocity data, time data, and also satellite related data. And this is how the sentence looks like, the NMA output. It starts with a sign called $, and then we have this GP, two letters, $GP, and we call this talker ID. And then we have this sentence header, sentence ID, like a GZA or GSB, RMC. There are so many, so please refer this NMA document in the internet, so it's available. Or it's available from the manufacturers, so they have mentioned in their user manual. So if you look at any GPS user manual, they provide this information, because they output this information to tell you the position data, satellite related data. Yeah. So this is how this sentence, for example, this is a sentence, how it looks like for GPGZA. And this tells you that this is the data for GPS, GP for GPS, and GZA is a position data, fixed position data. And then next we have this 123519 is the time in UTC. Okay, it's not your local time, it's the UTC. And this is how we read 12 hours, okay, hours, minutes, and seconds, HS, MM, and SS. And this is latitude data. So you have to read this as two digits, 48, this is degree, and 07.038 as a minutes, okay, degree and minutes, no seconds here. So 2 digits and the rest is a minutes. And this is telling you northern hemisphere or southern hemisphere, north south. And for the longitude, you have to take 3 digits, 011 degree and 31.000 minutes, and east or west. Okay, this is how you have to read. So don't read as 4,807. It gives a wrong value. And then this will tell you the fixed quality. So when the receiver compute the data, so it tells you how the position data is computed, whether this is using the standard positioning service, GPS, whether this is from DGPS, or whether this is a PPS, okay, RTK or float. So this type of information you get it. And then if you are going to do the high accuracy for processing data, then you have to exchange the data among the receivers, because to do the high accuracy, you need the reference data, the base station data or the course data, which is coming from maybe the service provider or somewhere else. So you have your own observation data, you have to remove some errors, and you need the correction data. This data is coming from somewhere else, but that source of data may be from a different receiver. You may be having a receiver A, but your other reference data is coming from receiver B. So if they provided data in their own proprietary format, so the system cannot read the data. So what they use is all this proprietary format is converted to RINEX. This is a receiver in that an independent exchange format, and this format can then. This is a sort of industry. This is an industry standard. So all the softwares or the system in GNSS system, they understand the RINEX format, and they know how to read and write this file. So if you getting the data from other GPS receiver, so you get most probably you get the data in the RINEX. Yeah, and it has 2 types of files: observation file and a navigation file for the satellite related ephemeris and the clock data, or file for the observation data to calculate your position. Okay. And this is just the example of the RINEX navigation data. So this is all the satellite orbit related data. So this satellite orbit related data and time data are required to compute the satellite's position data. Okay, in the slide we saw before that you need to compute the satellite's position data at that time. So at this is satellite number 32. Time is 17:05:01:01 and hours, minute, second. So, and these are the orbit data at that time, and some clock errors here included. So the software, the system reads all this information for this satellite at this time, and then it will tell you what is the position of this satellite at this time. Okay, this is how it works. Okay, so this is the end file, and then we have the observation data, and this observation data includes the distance between the satellite and the receiver here. Okay, so these are for each satellite at that particular time, and this this is off. Okay, this is the header, and this is the actual data, okay, for this UTC time, and these are the pseudo range, so the distance between the satellite and the receiver for different types of signal, L1, L2, and also the carrier phase, how many number of cycles, okay, L1, L2, L5. So these are the things that comes from the satellite to the receiver in the RINEX format, and the software interprets all these. So you don't have to manually do anything this, but we need to understand, because sometimes you'll be looking, working with these type of RINEX files, and then sometimes you have to, if there's an error or something is wrong, you have to see whether this RINEX file is correct or whether there's some problems or something is missing, because most of the time what may happen is this is a simply ASCII file. So during transferring or sending the file, if you open the file and if you by mistake just put enter or space here, so this will destroy the whole data. So your software cannot read it properly. Okay, it's a bit vulnerable. And this is RTCM, means this is another data format to send the correction data from your base station to the rover, from your course to the user in the field, to give a high accuracy doing the RTK and the centimeter level of data processing or data observation. So you need to send some correction data from your base station or your course station to the user in real time if you want to do the real time application. And this is done by using the protocol or the format called RTCM, and we have different types of the sentences here to send the different types of correction data. So the receiver will have this type of capability. You just tell the receiver you want to do real-time correction. So the receiver will set up the necessary sentences to be broadcasted for you. Okay. And then we have this coordinate system. So this probably all of you know, latitude, longitude, and height. So GPS uses a type of spherical coordinate system to give you the output. So you will see the lat, long, and height all the time you're getting. So okay, this is the spherical coordinate system. And then also GPS internally use the ECEF, Earth Center Earth Fixed Coordinate System, to do all the computations, the mathematical computations. So because it has to know where on the Earth is the receiver at that moment or the antenna at that moment. So if the antenna is here, it has to know where is it on the Earth. So it needs a model of the Earth. So this model of the Earth is given by giving the radius, and there's the elliptical, the orbit model we call the datum, and all these geoid values and so on. So we have Earth model based on some datum, and then we have different parameters, and then we have this type of coordinate system that the GPS use it internally to compute, and it can output the position data using the ECEF or using this type of a geodetic coordinate system, latitude, longitude, and height, or it can output both, or it can output in a different coordinate system, UTM or another local coordinate system, but that you have to tell the receiver and set some parameters. By default, it does not. It just gives you the lat long height or ECEF or both, but they are based on the WGS84 data. Okay? So GPS by default use the WGS84. And these are the mathematics to convert from one system to another system. So these are just the references, so you don't have to do anything on this. Okay, so this is how the GPS uses its coordinate system to give you the lat long height. For example, you see it uses a WGS84, and this is for GPS, so it's fixed. It doesn't use another system. So all the coordinates are computed based on this by default. And unless you request the receiver to output in a different datum, like if you are working in Asia, so many countries in Asia, there is Everest datum. So if you set your datum as Everest, then the receiver will convert from WGS84 to Everest before it outputs to you. So you have to check the receiver setting, how this is done. Otherwise, if you are getting the coordinate output in the WGS84, latitude, longitude, height, and if you want to overlay your existing map, it does not overlay, it doesn't match, because normally the maps in any country, they use the local coordinate system or the local the geodetic system. They may not be using the WGS84 for the maps, because this came only when GPS was developed. Maps were existing many years before the GPS, so they have their own coordinate system, their own data, and they have a different parameters. So these datums will simply tell you the model of the art. So what is this semi-major and the minor axis of the art? So this tell you the shape of the art, the ellipse, okay? Mathematical model of the art. So if you use the WGS84, these are the values. If you use a different one, these values will be different. So you have to check in the map or your existing data whether these values are same or different. Okay? And another one, this I explained many times also, about the height, and the GPS doesn't give you mean sea level height. It doesn't. It gives you the ellipsoidal height. Okay, but what is ellipsoidal height? So for example, we model the art like here. We have this ellipsoidal model of the art using the WGS84 datum. That means we take art as a very smooth surface, okay, like this ellipsoidal surface. But in practice, it is not like that. We have this very up and down, this geoid surface, which is related with the gravity. So it's a sort of a same gravity area. And we have sea, okay? But we don't have sea everywhere. We have mountains, land area, and so on. But if there's a sea, this will be probably the same surface. Sea level will be your geoid. And if there's no sea, like a mountain here, okay. For example, if we don't have a mountain and if there's a sea, so the sea level will be like this red line. Okay? This is what this geoid surface is telling you. And if you want to know the ellipsoidal surface, because GPS computes the ellipsoidal height, so this is at the peak of the mountain. You are here, and you measure here, put the antenna, and you get the height from GPS, and that height is computed based on this ellipsoidal surface, because GPS uses the ellipsoidal model, the WGS84 by default, and this will tell you, okay, you are so many meters above this surface. Okay, this is what you get. But we are used to it, the mean sea level, so we need the mean sea level. We don't know the ellipsoidal height. I actually don't know how many meters you are above the ellipsoid, but we really need to know this geoid height or the mean sea, the height at here from this geoid, okay, from this red surface. So this we need to compute, and to do that we need the gravity data and so many other different types of survey and all. But these data are approximated global data is available, and these data are some receiver manufacturers, they put in the database of the receiver so that the receiver can convert from the ellipsoidal to the mean sea level by using this n value. Okay. And this N is now computed. The MSL is computed like this. If you already have H from the GPS measurement, and then you subtract this N value. Okay. And in the case of N, if it is below the ellipsoidal, so this is negative. If it is above, this N is a positive. Okay. So here is the example. So this is how you get the mean sea level. And in the receiver, so you will see this type of output here, mean sea level and the geoid separation. Okay, so and by looking at this NMA output, so these are the NMA sentences, and you will see this type of output, and then you will know how much is your ellipsoidal is not mentioned because it actually we don't know. So we know the geoid separation, the difference between the ellipsoidal height and the geoid height. And then using this, we calculate the mean sea level. And mean sea level is what we know. Okay? Then this simply tells you that you are 54 meters above the sea level where you did a survey. And looking at this, so you can estimate, okay, predict whether there will be a flood or tsunami and all. Then we know how high you are with reference to the sea level. Okay? So this is what the receiver does. Okay, I skip these ones, and then for the errors, so again, I put these slides and go very quickly. So in GPS, most of the time we get this type of error. Means we have a true point here, the accuracy with the true point, but we'll have some sort of bias always. And this is if you just observe the GPS for 24 hours and if you compute the mean and standard deviation, probably you get something like this. You have very small mean value, I mean very small standard deviation value. So you think this is very highly accurate, but you may have some bias, some offset from the actual true value. And this bias has to be removed to have a very good accuracy. Okay, so all these error removal can be done in the RTK or DGPS or PPP processing. So in the last lecture, last training, we did all these discussions and the demonstrations and the participants. So we showed to the participants how this can be removed in the RTK Leaf software in the data processing. So these are the 4 cases that we have. Probably we have this one. So we would like to have this type of scenario. But in order to do this, you need to do some error removal technique. And this is important for you if you want to purchase the receiver. So you have to look some of these error parameters. So they will tell you their accuracy of the receiver in terms of the RMS value or 2D RMS, CP, 95% probability, or SCP, 3-dimensional, this accuracy value. So all these values, so it's up to the manufacturer how they want to rate or show their receiver's performance or quality. Whether they want to use CP or 2D RMS, it's up to them. But sometimes they don't write anything. They just write, okay, my receiver can give you 30 centimeter accuracy. That's all. And then you really don't know what does it mean. So when they say 30 centimeter, whether this is CP, RMS, 2D RMS, or R95. Definitely it's not R95 because it's very difficult. And then probably they will be talking about RMS or CP, probably. Okay. Most of the case they use a CP, but they don't tell unless you ask. So ask them what are these values, whether this is CP value, RMS value, or 2D RMS. These are some popular accuracy or the indicator used in the GPS technology. Okay. And another important parameter is this time you see the TTFF or like a true time to first fix. So any GPS receiver when you purchase, if you look at the receiver, they have TTFF time. But I don't think that really makes a very big issue for ordinary receiver unless you are going for a very like a car, this ITS type of receiver where they need a very quick start. When the car comes out from the garage, it should give you immediately the position data. Because GPS by design, it will take you at least 30 to 36 seconds to give you the first position data. This is the time. True time to first fix means once you put the receiver power on, you have to wait some time. But how long you have to wait? It depends where you are located and how good is signal and so on. In the best case, you still have to wait 30 to 36 seconds to get the first position data. Okay. If some receiver they write maybe 10 seconds, it's not true. Then they really don't know the meaning of TTFF. Okay, it will be above 30 seconds because the navigation message is one message is 6 seconds long, and to compute the position data, you need at least 3 frames of that, and that will take 18 seconds. But when it comes from the satellite to the receiver doesn't know which frame is coming. So it may be frame 3, it may be frame 1, it may be frame 4, frame 5. If it is frame 1, so probably that's the best case, but it's not always true. So in the very beginning, the receiver has to wait all the 5 frames. That takes 30 seconds, and then it needs some processing time. So that's why we say the cold start TTFF is 30 seconds plus. Then this may be shorter, maybe 12 seconds or 10 seconds or 6 seconds, depending upon how the manufacturers they define these terminologies. But at least this may be just a few seconds, this may be 6 seconds or more, but this will be definitely 30 plus seconds. Okay. Then there are many other standard accuracies that we'll see in the technical specs at the end. So this is what I'm talking about TTFF. Okay. So let me take, we will break at 5 p.m., but let me take a few minutes of break for myself. And during this, before I go to another presentation about the applications, so if you have some questions, so let me know at this time about this long presentation. Okay, I see. Okay, I think there are some questions in the chat. Can we detect radio frequency effect in GNSS data? Yes, I have another slide for this. So we'll talk in the security issues. So I have some slides there. Actually, I have a very nice this impact. Can it possible to use Gnss in Africa? Sorry, I don't have the exact answer for you about the accuracy level and all, but definitely Gnss is available in Africa. That I am sure. In Ethiopia, I think you can use it. I think you can use it. Need to check the Gnss visibility map. I can check during the break, but accuracy, I don't know. But whenever you use in general, the SBUS accuracy is about 1 to 3 meters accuracy. It's not giving you centimeters, so it's about 1 to 3 meters accuracy SBUS. But SBUS is not only accuracy, but also its integrity, means you can rely this signal, GPS signal or other navigation signal. So that's the purpose actually. So accuracy is improved as well as the integrity or the service level, okay, for aircrafts. Is it possible for RTK software to be embedded in GNSS receivers? Yes, of course, yes. So many receivers. So, but these receivers should be RTK capable. So in order to be a receiver RTK capable, it should output necessary data, the raw data, carrier phase data, code phase data, and some other information from the receiver. And it should have this software to do this type of processing. And also it should have some data format, reading and writing, like RTCM or RINEX. So this is what we are looking in the technical specifications. So what type of receiver, the capabilities of the receivers. Okay. So we'll have another detailed discussion in the later presentation. So that's all. I think that's so many. Okay, so let me go to another presentation on the applications. So this will be very quick presentation, but okay. So I have 3 or 4 slides with all these text only, and then few with figures. So many of you probably many of these applications, and probably you are using it as well for GNSS or GPS. Of course, surveying, mapping, and geodesy is the main application. It's very widely used for that, so I don't go to the details on that. But for transportation now, car navigation is one of the applications. Then the new thing is coming up, ITS, that's Intelligent Transport System. And I think you know this keyword ADAS, that's Advanced Driving Assistance System, like a parking, lane changing, all these safety related navigation in the car, obstacle avoidance. So all these are based on the GPS, but not only GPS or GNSS, they have many other sensors, laser, microwave, radar, and so many other sensors to detect, but GPS is one of them. So you do need the GPS to get the position data from time to time. And this vehicle to X, V to X, V to V, vehicle to vehicle to anything. Again, this is to the V to V itself doesn't use the GPS data or GPS signal. This is to send the data to communicate the information between the vehicle to vehicle to tell that if there's an accident, then that vehicle can relay the message to other vehicles behind or in front of that vehicle. Or the vehicle can communicate with a pedestrian on the street or other mode of transport on the street, like a bicycle. Like a vehicle can send a warning signal to a pedestrian or bicyclist on the road that the vehicle now is going to take a turn, so please take care. But this is on the based on the communication signal. But they need to know the position data. So the vehicle needs to know its position at a time. The vehicle also needs to know the pedestrian position at a time. That's the reason why they have to have some sort of a GPS position data with a good accuracy level. Okay. And road pricing and toll. So this I will show you more detailed slides later. So congestion management, okay, traffic congestion management in the railway. For security and safety and all these the railway, like in the USA, the trains are so long. maybe it's 1 mile or more than 1 kilometer long, and the driver need to make sure that all the cars are intact. It doesn't miss any car, even for that type of simple things, because the driver can't see the last car. Visually, it's almost impossible when there are tons. So to make sure that all the cars are intact and no accidents, nothing has happened. So they use a GPS to make sure that everything is okay. And in marine AIS, VMS, so AIS is auto identification system, VMS is vessel monitoring system. So for the big boats, 300 big vessel ships, 300 tons or above, by regulation, it's mandatory that they have this VMS or AIS system. But for the small boats, it is not mandatory. It's not required. But some countries, they already adopted GPS-based system to be necessary to include in the small boats as well. I think this is basically for the fishing boats and maybe like some other pleasure boats where the life of the people on the boat is a high concern. Okay. And aviation, so in the airline, this S-Bus and G-Bus is very important. They're using it and with the very strict guidelines. And this is completely new field that's coming up after drones getting popular. So they are using the GPS with the high accuracy to have mapping or the aerial photo taken without using the ground control points. That's a very easier now to get the high accuracy position data, and you do the direct georeferencing. And this is now already implemented in Europe, eCall or ERA GLONASS in Russia. So I think from last year, so all the cars to be registered from last year, they must have eCall capability. This means if the car has an accident, the driver may be unconscious to call the emergency service. So the vehicle will send some signal automatically to dial the emergency service. And this will send the position of the car at the time of the accident. So the emergency service providers, they know where the accident is. I think this is already legally implemented also in Russia. Now, any car that is made in Japan to export in Europe, they should have this facility included in the car as well. Okay, so this type of things, it's based on the GPS or GNSS. And there are some companies that use the taxation or insurance, like for a vehicle, they say, okay, you pay just for the distance you drive, pay as you drive, or so these are also the control by some companies using the GPS for trucks and so on. And there's legal and law, fishing zone management, illegal fishing. I'll show you some slides later for illegal fishing or zone management. And then for crime prevention, like for security purpose, some people like criminals are controlled by putting the GPS tag on their legs so that they don't go out of in the USA. So this is very common. Okay, you can be arrested. You can stay at home, but you are not allowed to go outside of the home. Okay. And this agriculture, precise farming is one very huge business in the USA and Europe, also Australia, New Zealand, but they need to control their machines, tractors very precisely. So again, I have one slide for this. I'll explain why this very high accuracy is required for precise farming. And all these, okay, so some of them are new. EWS, I have a separate slide.
Gnss?
Yes.
I'm very sorry, but you are not displaying those slides.
Oh, sorry. So I'm still sharing the old one?
Yes.
Let me know in the very beginning. Okay. Now, how about this?
Not yet. Yeah,
right.
Now we can see them.
Okay, sorry. Somebody has to let me know because I'm concentrating on something else. Okay, so okay, now you can see, okay?
Yes, it's fine now, Gnss.
Okay, thank you. Otherwise I would be going like this. So you see the ITS, so all the keywords that I was talking here, so please look at this handout later. Then we have this one. Okay, fishing zone, illegal and all, but these are only the text, so I'll be showing you. And this is a little bit important. I mean, a little bit means probably many of you don't know whether how these are used here for all these things because they don't use the position data. But GPS also provide very highly accurate timing data, time data, because GPS uses atomic clocks. So the time coming from GPS is extremely high accuracy. And these timing signals are used in the telecommunication to synchronize the cell tower, especially this is a must in the CDMA. And also in the 5G, the new system, this time synchronization should be within, I think, the 100 nanosecond or like that. Okay? So it's a very strict requirement, and that can be provided by Gnss system. And for power grids to phase synchronize between the different power stations when they send to the central grid, they have to do the phase synchronization, and this is done based on the timing. So GPS is also used there, and in the huge financial transactions in the banks and the legal documents or shipping, so on. So time is again very important. So they also use the time. So there are very special devices available for this type of services or business, and they use a GPS signal. So if there's something wrong with the GPS signal, so these things will have a huge problem. Okay. I'll skip this one. So these are some applications like RTK. So field survey. This is the PowerPoint slide from our colleagues in the Tokyo University Marine Science, and it was presented last week. And now this machine control, you see, they need a very high accuracy machine control, and they have sensors, different types of sensors, and GPS is one of them, to tell the system how much it should dig to make some volume of the the pit or in the mining. So it's all done automatically. So but they need a very high accurate sensing of this using the GPS data. And the drones, so automated this flying or taking the pictures and all. Okay. And these are for the maritime in the sea. So the automated, now also the ships, so it's automated driving or automated navigation of the ships. So you don't rely only on the captain, but you can also do the automated. And this type of things are basically based on the GPS plus other sensors. They have other sensors, but GPS is the main, and they need a very high accuracy as well. And this type of a precise agriculture now is getting very important to have a high accuracy, because like if you put some seeds here in these things, and you need to put water and fertilizer wherever you have seed. So if you have a seed here, and if you put water here, so you lose it. Okay, so your production will be decreased, and you lose a lot of money. And when you consider very huge fields, many hectares of field, and also you need a lot of manpower to drive the tractors. But like in Japan, so not so many people to work. So they want to automate this type of tractors driving. So without the driver, it can go day and night and go to the field and do the all plowing and all these things and come back to the garage, return automatically, charge the system and go back again. So this type of all automated driving, it requires very highly accurate position data. And for precise farming, the position requirement is within 5 centimeter. That means plus minus 2.5 centimeter. Okay, so this is 3 to 5 centimeter of very high accuracy is quite difficult. But today's technology called RTK or PPP RTK, or in Japan we have a CSIS. They can provide 2 to 5 centimeter of accuracy. And when you have this level of accuracy, you see something like these green dots. So if you don't use this high accuracy service or system, you will be like a red, and it doesn't help, because this tractor has to go to the same area to put the fertilizer, to put some chemical or water, maybe after a few days of interval. So it goes to on day 1, and after 2 weeks, day 15, when it goes back, so it should follow the same track. Okay? And that must be very, very precise. So this is a huge business in the USA, Europe, and other countries, how to automate this one. And this is one case. So I'm giving you some real example how this is being used in the practice. So Queensland in Australia, they started monitoring all the fishing boats. So they made it compulsory that all the vessels, whether it is small or big, if it goes to the sea, it must be monitored, and they should have a GPS receiver, and they should send the data almost in real time. It can be monitored in real time. Now, all these boats, the small boats, they have a GPS in the Queensland, and this is made it from January 2019, and and it's already implemented in the beginning. So people were not happy, but now it's already done, and they are doing a very close monitoring. So you have all these references. So please check how they are doing and what type of regulations they have. So very detailed information is available, and you can see these videos on YouTube, so why they are doing and all. But this is, I think, a very, very important thing to do, this type of a marine or ecology, protecting the ecology, protecting the overfishing, and so on. Okay. And this is one case in Indonesia, like in Bali. I went to this one, and these are the traditional fishing boats in Indonesia, very colorful. But in this area in Bali, they could not catch fish for almost 1 year. So they have not been to the sea for 1 year. They don't know why the fish they cannot catch fish, and it may be overfishing. It may be the temperature. It may be some environmental change, something like that, but we don't know the reason. So the recommendation now, we are recommending, okay, why don't you do the monitoring of all these fishing vessels, boats, not the vessel, the fishing boats. So why don't you put a GPS and see where they catch, where they cannot catch, where they go and all. But this type of discussions now going on, they're in reality. And we do lots of workshop or training with the stakeholders and also the fishermen, local fishermen, because fishermen are they are very hardworking, but they are not very happy to put the GPS, because this is to reveal their secrecy or their expertise or know-how where they can catch the fish, because this is very much the know-how of the fishermen, and they really know where is the fish by just smelling in the sea. From the smell coming from the different direction, they can see, okay, this area they have fish, and they don't want to put with the GPS. So, but the government has to put some regulation to make all these type of information anonymous, or maybe protect some of those know-how or some other informations, but just to monitor or control the illegal or the overfishing and so on. Also, many illegal boats come from outside of India. In Indonesia, that's a huge problem, big problem. So the government is very much serious about how to control the illegal fishing. So GPS will be one of the tools to do that. GPS alone cannot solve, but GPS will be the minimum requirement for this type of problems. Okay. And then there are some other possibilities, new applications, which is not related with the position or time directly, like sending some warning message from the satellites to your mobile phone or your GPS receiver. Like what happened in Japan when we had a huge earthquake in 2003. So all the mobile communication, so it did not work for some time. So how do you communicate? How can the government send the information to the public? Then the one solution was to use this GPS satellite, or in Japan, QGIS satellite. So now QGIS has that capability to send the early warning system. So if earthquake is predicted or tsunami is predicted, so it can send a warning message. And this signal is now already being broadcasted. Now it's coming every day. If there's no warning, so it may be a 000. And when there is a warning, it will send some code. And if you look at that code, your software, your receiver can interpret, okay, this warning is for tsunami, or this is for flood, or this is for earthquake, and so on. Now this is now being investigated and being tested in Japan and maybe also some other Asian countries. And also we are working on this to see how it works. And also Europe is going to do very similar thing. You can see this type of information in the last week presentation on QGIS as well. So Galileo will implement this early warning and they are collaborating with the QGIS to see how to make this type of standard. And also Galileo has a very nice, this search and rescues or this signal to, so if you are in a problem like in the sea, so if you are drowning, your vessel is sinking, so you can send a distress signal. Currently you need a very special, this type of a special device, but now you can use those devices or other devices to send the signal to the satellite directly from your SAR compatible, using the SAR compatible signal from Galileo. And probably this will be implemented in other satellite systems as well. Okay, so these are some details about the early warning system. So I don't want to go all these things, so please check the handouts. So this is one example for Indonesia, like they already have this type of early warning system, except this QGIS, this one. So this is already there for the buoys and all to detect tsunami, because you see in Indonesia has lots of earthquakes and tsunami problems and so on, this region. So Indonesia, Thailand, and this region is very vulnerable to this type of a natural disaster. So they already have this type of system, but the problem is it doesn't go to the last mile. So when there's something happens, so how to send this information to every people in the affected area, that's very difficult, because due to the power breakdown and all, mobile phones don't work, internet doesn't work, and so on. So you can't communicate. Okay, but if we have this type of a broadcasting system, the satellite can broadcast the signal directly to your mobile phone. If your mobile phone has a capability to receive this signal with the GPS or QGIS capable device, then you can receive the information from the QGIS directly. So it doesn't matter whether your mobile phone, the communication signal works or not. So as long as you have a battery to mobile phone, so even if your communication doesn't work, you can still get the signal from the satellite. So you know you will get the warning message once it is broadcasted from here. So this type of things can be implemented in future or in very near future. And this is one example for dynamic road pricing for Singapore. So we are proposing this type of things. So if you've been to Singapore, you know that they have electronic road pricing. And this ERP it's actually a physical gate, very huge gate, and they have a sensor. And when you pass, so your car has some device to get a signal from here. So based on the day and time and the rush hour, you have to pay if you enter this road. So this is the system in the Singapore, and they have this type of gate in so many places. So once you ride a taxi, you pay the taxi fare, and then you also pay the ERP price on top of the taxi fare. Okay, and that fare will change depending upon the time and the congestion here. But the Singapore government wants to extend this to many other roads, but it's not easy because they have to put this type of gate. Is too much, too expensive, huge, and they are saying that it's not beautiful because it will see the block the beauty of the open sky and all. So they don't want this type of gates. So our proposal is, okay, you put the GPS receiver on a car and just using the GPS, you charge it. But there are other problems because if you use a GPS alone, it may be jammed, it may be spoofed, and you cannot charge or you cannot collect the toll from the car. So we have developed or made some systems like this one, authenticating the GPS signal, whether this is a spoof or not, so we can test. And based on that, then we can charge the user how much the user has traveled. Okay. So this is a one demo or prototype app we have developed. So we have doing some sort of a POC and also collecting the data and doing lots of tests on that and see how it works. Okay. This is one very important example. And this is also necessary to do the traffic congestion management and also monitoring the traffic. So how much traffic is there, which route you should take, and how much charge you should collect. And this is not only Singapore, but I think other countries are more severe, like Indonesia or Thailand or probably in Malaysia, many Asian countries. So because it's getting very fast development, and that means a lot of traffic. So it's hours and hours on the street, and the car doesn't move at all. Okay. These are just some test data from there. Okay, I just skip. So some keywords, so I just put whatever we have, so you can look at these keywords and see a lot of possibilities from here. Okay. And actually, we have developed a sort of a prototype apps to collect the data. Like we already developed this type of app for Jakarta city. We have a road network data already input in the digitized in the database here for Jakarta, Bali, Singapore, Ho Chi Minh, Cairo, Bangalore, Kathmandu, and Baku. So anybody from these countries, if they want to do a pilot project, so we can do at least collect some data immediately and see how it works. Okay. So these systems are already in our database. We already made a database for doing some sort of pilot project. But unfortunately, due to COVID, we could not go to any of these places. So otherwise, we would have done some pilot project with these countries or universities or organizations, whoever is interested. So I suppose that some of our participants are from these countries: Indonesia, Vietnam, Egypt, India, and Azerbaijan. Okay. So there was a request from Azerbaijan, so I put the Baku as well. But we could not do due to COVID. And of course, we already doing something in Singapore, and very soon we are going to do in Indonesia, Jakarta and Bali, Singapore, and maybe also Ho Chi Minh or India. And of course, Egypt, they are waiting as well. Yeah. Okay, that's all for these applications. And then, so let me take some questions if you have sent in the chat. Otherwise, we'll take a break and we'll meet after 40 minutes, I think. Let me see, there are some questions here. Oh, Adric. Oh, sorry. You could not see the slides. Thank you. Are there many researchers in the field in Africa? If yes, please provide the link. If no, is it possible to research in the field in Africa, considering that we are developing countries? We don't have much relation with Africa because it's quite difficult to get information as well. But we do have some work or some relation in some African countries, especially Mozambique, Rwanda. For GPS, yes, Mozambique and Rwanda, but we have other research or other work related with this other disease like what was that, SARS and Ebola during that time. So we were doing some collaboration or some joint research studies in those countries. Yes, but not with the GPS directly, but GPS is related anyway. So at the moment, we don't have very close collaboration with the African countries, except Mozambique and Rwanda. Yeah. Okay, there are no other questions, so let me take a break. And so may I ask Patrick, so what time we should come back?
I would say according to the agenda, 8:50. So 10 minutes before 9 unified time, UTC.
Okay, UTC time. Okay, so that's
roughly in
after
40 minutes.
Okay.
Exactly. Yeah.
Okay, so let's take a break for about 40 minutes, and after the break, so what I will be presenting is, let me see what I will be presenting so that you can prepare in advance some questions, and I will share these slides right now during the break, and let me see what I'll be doing after the break. So okay, there are three topics. One is the low-cost receiver system, and GNSS security issues, jamming, interferences, spoofing, and the important topic is on the GNSS specification, interpreting the specification. And I will spend more time on that, and the other things, low cost and the security issues. So I'll have a very brief discussion, and during this break I will share the PowerPoint. So I think you can get by email or you can download. So please check, and so you can have more discussion on that if you have a PowerPoint slides. Okay, so thank you very much. So Patrick, if I send the, but how can we share the PowerPoint slides now? Shall I send by email or we put on the website, because that will take some time?
Yes, no, you please send them to me, and we will make them available on the USA website. Okay. For download. I think that's the easiest way. I can then also send out the link to all the participants. Mm-hmm. But it will be at the same location where they registered. But yeah, we'll inform accordingly. Okay.
Yeah, that's fine. Thank you. Thank you. Okay, see you after 40 minutes.
Thank you, everyone.
Yeah, thanks.
See you. Hello, everyone. It's 10 a.m. here in Vienna, and I would like to thank you again for joining us to the second part of today's session. Dinesh, in a minute, will continue with his presentation and give a brief overview of low-cost, high-accuracy receiver systems, RTK and PPP, as well as hardware and softwares. So we are working on his presentation, which will be posted on our website, and you will be informed by the end of the workshop where it is posted, and get the direct link to the presentation. Also, we would like to let you know that we are preparing the feedback questionnaire to get the overview of the organization, such kind of the session, and whether it's needed to be organized in the future and what we can improve. So we will, at the end of the session, we will send you the message and give you the link to this questionnaire. With that, I would like to invite Dinesh to continue his talk on this topic. Thank you, Dinesh. I see the message from Patrick that today's presentations are now available on the website, and he provided the direct link. Thank you, Patrick. So Dinesh, please, the floor is yours.
Yeah, okay, just a few minutes. Hello, can you see the slides now?
Yes, Dinesh, just
Okay.
have to change it to the presentation mode.
Yeah.
Thank you.
Okay. So now I'll be talking on 3 more topics. One is this low cost system. Also, I did last week for the training group. This is the contents are more or less similar. And then I will do one more new topic on the security or jamming interference spoofing issues. And then finally, we'll do more on the technical specifications, interpreting and understanding the meanings of that. So let me start this one first. So many of you always consider about the price. For example, if you need to buy a receiver, so how much it costs. Maybe a few dollars, $10, $20, or $100, maybe very expensive, more than $10,000. And as you see, we have receiver of all these categories, or even less than $10, we have it. Basically for the receivers for mobile phone or some embedded system in some other devices. So it's not the receiver, but it's a chip or module that's just a few dollars. Okay, so we have all the range from few dollars to more than 10,000 or 30,000 or even 50,000, like that. Very, very high end, sophisticated this choke ring antenna, and the receiver systems and software. So they are quite expensive. But anyway, so we have all this, and it depends on the application and your requirement. And also the accuracy we can get from this, it varies. So maybe a few millimeters, centimeter level at least. And then maybe a few meters. That's a very standard receiver, maybe within 10 meter. That whenever I say this means it's a guaranteed. Okay? Sometimes you get a 2 or 3 meter, sometimes 5 meter, but we can't guarantee that in 100%. So this is almost not 100%, but maybe 1 sigma or 2 sigma or 3 sigma of this level of accuracy. So that we need to guarantee. And also then when you are doing as like a decision maker, so what type of applications you are going to use for these receivers, and what are your accuracy requirements? And this accuracy requirements are very, very critical, whether you really need a centimeter accuracy or not. Many people, when we talk about accuracy, they always ask, can I get a centimeter level of accuracy? And it's not always possible. And then you may need a very complex or high-end receiver in some cases, depending upon your working environment where you want to use it. And also, how do you want to log the data, whether you are logging the data in the static mode or in the dynamic mode on the car or tractor or machine. So based on these operating mode or the data logging modes, so the receiver or the system you require will be completely different. For example, when you put on a machine, the machine may have a vibration. So the receiver must be able to retain, should work even that level of vibration or shock. So all the receiver doesn't work in the same condition, in the similar condition. And also real-time observation or post-processing, again, it depends a lot if you need a receiver for real-time. So it should have a real-time correction data, this input interface, RTCM or like that. But if you are working for post-processing, then you can just log the data and you can do the post-processing later. Okay. So I'm talking about very high accuracy, the real time for centimeter. But if you are not looking for centimeter of high accuracy, like a standard observation, then you don't need anything. You just buy any receiver, put on the power, you get the position data. That's all. And this is about the high-end survey grade receivers. So now we'll see the difference between the high-end survey grade or low-cost receivers. So what will be the differences? Basically, when we say high-end survey grade, so the receivers will be, at least they are capable of multiple frequencies or, of course, multiple systems: GPS, GLONASS, Galileo, Beidou, QZ, and navigation, Navi. And they will be capable of receiving different types of signals, L1, L2, L5, or L1, L2, L3, all these different frequencies. Maybe all capable, maybe not, only L1, L2, or L1, L5, like that. But these are the signals available. Okay? So in the signal spectrum, you see for L1, L2, L5 and L6. So different types of signals are available for different purpose, different applications. So you need to know which one to be used. But basically this L1 and L2 is a very, very common signal at the moment. So any survey grade receiver, you will probably have L1 and L2 signals, CA. And the new satellites, new receivers, they will have also L5, L1, L2, and L5 will be quite common. But this E6 is still very few in the market. It's not very common at the moment because there are no such signal that can be used at the moment. So Galileo just started high accuracy service. QG also started the service, the signal broadcast, but the receivers is not very common. Very few receivers available, and I will show some receiver types for the low cost for L6 as well. Okay, but these type of receivers that's capable of all these, maybe I think you have to pay around at least $3,000, so it may go up to 30,000. Including everything, I mean the receiver, antenna, and necessary hardware, other software. So probably the price will be around 3,000 or like that. Maybe some modules, it may be around $1,000, so less, around 1,000. I don't think it's less than 1,000. But anyway, the price will go up. Okay. And for low-cost receiver, so basically the low-cost receiver nowadays also capable of multi-system. Okay, GPS, GLONASS, all these systems they are capable, but it depends on the receiver whether they can work all together or whether you can choose only combination of some of these satellites. Maybe, for example, you can use GPS and GLONASS and Galileo together, but you may not be possible to use all the signals together because there are so many signals, so many channels, and it depends how many receivers how many channels the receiver can accommodate. Some receivers have limited capacity in terms of CPU, processing power, and the memory, so they can't process the signal from all the satellites, all the signals at the same time. So in such cases, you have to limit within GPS, Galileo, and Beidou, or GPS, Galileo, and QG, something like that. Because if you have a quite good number of satellites, I think you can skip one or two different type of systems depending on your location or working environment, whether you are going to use for RTK or whether you are going to use for PPP. So you can select based on your navigation, your observation method. You probably can exempt or remove one of them to not to observe, so that you can have you can use the low cost receiver. Okay, so basically the low cost receivers nowadays, so they are capable of all these signals, and some low cost receivers also available in the L5 band, like some chipsets in the mobile phone from Broadcom, so they can receive L1, L5. Okay. Also some others for Navic, they have a signal in L5, so it can receive L1 and L5. So already in the market, so in the mobile phone, like Xiaomi Mi 8, and they already have L1, L5 chipset, and also some Redmi mobile phones from Xiaomi, they have L1, L5 chipsets inside to output both position data computed from L1 and L5. So it's coming up even in the low cost. And when we say low cost, so at the moment the cost is around maybe $300 or less, or maybe more. So what is the definition of low cost? So for different people, maybe different meaning, whether $1,000 is low cost or $3,000 is low cost or $5,000, it may be a different definition. But for me, my definition is about $100, so it's still expensive for me. So my target is $100, including antenna, receiver, and everything. Okay, so that's my definition for low cost. So this is what I'm saying: $100, and should be able to provide accuracy better than 100 centimeter and should be very small enough, like 100 gram or like that. So 100, 100, and 100. So at the moment, we can achieve this better than 100 centimeter, 30 centimeter or 50 centimeter accuracy is possible, and weight is okay. But this price is not okay. Not at the moment, it's a little bit more than $100, okay? Maybe around $150 or $200. So at the most 300 with L1 and L5 or L2. Okay? So with around $300 to $500, we can have a multi-frequency. With the single frequency, this is about 200 or 150. So it's a little bit above this target. I suppose that this price will go down within the next, again, 1 or 2 years, because there will be more and more users. So more users means more production, and that will reduce the cost. So maybe sometimes we wonder whether this low cost, such a small system or device, whether it can still give you the very high accuracy or not. So that may be one concern we have. Then we have to look at the data or the technology, why we can do that. Okay. So first we need to see technically whether this is possible or not. Okay. And this is one data. So this is what we did, the exercise last week training. So we gave some sample data. So if you refer to our previous last week training data, you have all the sample data that you can do the same thing as we saw here. This is not just a imaginary. So this is the real data we logged for long hours, and without doing any correction, if you plot the data, it will be like this. So this accuracy, you will never get centimeter. It's not possible. Even if you use a $10,000 receiver, you will have the same thing. Okay? It may be a little bit better, but it will never be centimeter accuracy, even the output from a $10,000 receiver, unless you do error correction, error removal technique. Okay, so this is how it looks like. So this data, if we do some error removal, so it will be from these red dots to blue dots. Now we have a few meters of accuracy. You see, this is a 50 centimeter grid, and this is about 1 meter plus minus 1 meter. So we can guarantee about 3 meters of accuracy with this data. Okay. So this is what we mean by the accuracy is a few meters possible by doing the differential correction or DGPS using the code phase data. So this is possible at the moment. And if you do the same thing with the SBUS satellite, you will also have this level of accuracy. So about 1 to 3 meters of accuracy. Now, if you see these red dots and the blue dots, there's one significant difference here. If you take the average of these, okay, so you will get maybe this cluster somewhere over probably, so maybe somewhere over here. Okay, but your origin is somewhere over here or here. Okay, so that means although our standard deviation is good, so we have a bias or offset from the true value. Okay, so when we do this type of differential correction, we remove some of those errors, and then we also remove the bias. So this gives you much better accuracy. Okay, accuracy, also better precision and better accuracy. Okay, accuracy means this is the error with respect to the true value. So this result will be near to the true value. So you should do at least the DGPS. And the many receivers, a little bit of if you pay a little bit more, so you get at least DGPS capability in a very standard receiver. So they can provide this level of accuracy. That's much better than this one. But if you want to have a centimeter level accuracy, then you really need to do very complex data processing or data observation. And all the receivers are not capable of doing this. You need to tell or ask the provider, the company, to provide you a RTK capable receiver. Then the price suddenly goes up because it's quite complex, and you really need the reference data to do this. So you should also have a reference station somewhere to get the correction data. So you need 2 units then. Okay. So this is then you can get centimeter accuracy by removing some errors. Now I will show you what type of errors we remove and why we can get this centimeter level of accuracy. Okay. Now, before going further, why we can get, so we need to understand the errors in the GPS. So we have different types of errors. For example, satellite orbit error, satellite clock error. These are the atmospheric error, ionosphere or space weather related error, ionospheric error, tropospheric error, and multipath. So some of these errors like satellite orbit and clock we can remove. And this is actually a few meters of error here, 2 meters. This is approximate, okay, just approximate values, 2 meters and 2 meters. But these errors can be removed completely by doing differential correction. No, so not the difference, sorry. By doing the broadcasting this error from about the satellite orbit and the clock. So we can compute this error and send to the receiver. So we can eliminate this completely. But this one, we cannot. So it can be minimized, but it will never be zero. But with different disk correction methods and modeling techniques in the receiver, so it can be reduced. But it's a significant reduction. You see the ionospheric is quite large, actually. It's a few meters of error. So these values are just the example, and don't think this is the exact 2 meters. It may be 1 meter, it may be 3 meters, something like that. But some sort of standard deviation with some mean value with 1 sigma error is about 2 meters. But the point here is that this can be removed totally. This can be minimized. These errors can be minimized. And in order to do this, so we need some capability in the receiver. Okay, and this multipath we cannot. Okay, this is related with your surroundings. If you have a tall buildings that affect your visibility to the satellites, then you will have this. Okay. So we can, if they are removable, so we remove it. If they can be minimized, we minimize it. So these are the two things that we can do. So in order to do that, so we need a reference station somewhere. Okay, so this is the RTK method, or we call the differential correction method. For DGPS or RTK, we need a base station somewhere at a known point. So you put a station at a known point, and then you observe the data. Then you know how much error is here. Then you know these errors are coming from different sources, but you know the accumulated error. And then you send these correction data to the rover, okay, in the field. And also they should be looking the same satellites at the same time, so that they can observe like these common errors, orbit error and clock error, because it's the signal is coming from the same satellite. So whatever orbit error or clock error, satellite clock error it has, it will be the same for this receiver. It will be the same for this receiver. Okay, and if you put a receiver at a known point, so you actually know how much error is here in this satellite. Okay, but there are other errors like ionospheric and tropospheric, but they can be measured or modeled by using a multi-frequency receiver L1 and L2, because the impact on the L1, L2 due to the ionospheric we can measure or we can model. Okay, so we need a dual frequency receiver for that. And if we can do that, we can minimize those ionospheric and tropospheric errors. Okay, so by doing this, we can send this type of some correction data or the error information to the receiver in the field we call the rover. And this receiver then do the processing to have a high accuracy. So in that processing, we remove these type of errors, orbit error and clock error, and we can minimize these error. So your accuracy from few meters goes to the centimeter level. Okay, so this is what we did. So if you look at this data, your accuracy is few meters. So we remove orbit error, clock error here, and also remove or minimize the ionospheric and tropospheric error. Then from here we go to these green dots, that's just a few centimeters. So this is the processing in RTK. We call the real-time kinematic, but this is basically doing all these type of error removals and also observing the carrier phase data. So when you buy a RTK receiver, your receivers should be able to output this carrier phase data. All the receivers, they don't. Okay, So if the receiver doesn't output carrier phase data, it cannot do RTK. It can do probably only DGPS with the code phase data. So once you mention RTK, so the receiver outputs the carrier phase data, and you will be able to do all these type of processing either in real time or the post-processing mode, and the price goes higher. And this type of RTK, this RTK requires the base station here, and this distance between the base and rover is also, it's not fixed, but it's a recommended distance, maybe around 30 or 40 kilometer. And if you go very far, so the accuracy you can't have the same. Okay, the farther you go, you get worse accuracy. So the recommended is within the 40 kilometer. But if you want to cover the whole country with the RTK, then you have to put so many stations around the within the country, maybe hundreds of them, and that's too expensive in terms of the infrastructure cost and the operation maintenance. So to avoid this, there's another solution or another method to do this. It's called the PPP. So in QGIS, it's called the Madoka PPP and CSIS service. So two types of services, Madoka and CSIS. Also Galileo, they have this type of high accuracy positioning service, but they have another name. Is I think they now call SAS, high accuracy service. But basically it's doing the PPP. That PPP means precise point positioning. So what it does is it sends the satellite orbit and correction data directly from the satellite. Okay. So here we are sending the correction data from the base station, but here we are sending from the satellite directly. So you don't need this type of a base station now. Okay. So you can do without the base station like this. But the problem is that this correction data is sent in a different frequency in L6 band. Okay. That means you need a receiver that can receive L1, L2, or L5, and also L6. So at the receiver, it becomes a little bit complex, but receiver side, I think the price will go down as time pass by. So we don't have to be much worry about the receiver. As long as it can send the correction data from the satellite, it's much easier to work since you don't need a base station to put by yourself, or you need to get from some other station in real time. So as long as you see the satellite, you get a correction data. And another advantage of this is that if you don't see this satellite due to some reason, you can also get this type of correction data through internet. So they also have a facility to send this correction data to an internet or Ntrip server. And this Ntrip server sends the correction data to the rover if you can access the server through internet. Okay. So this is the another way of doing the high accuracy positioning service. And now this is available in Japan and Galileo. It will be available very soon. And we have developed some low-cost RTK system based on the low-cost receiver. Basically, we use a U-Blocks and we connect U-Blocks to Raspberry Pi, and you can display the data in the tablet because it doesn't have a screen, or you can put a screen here, display here, and you can get the correction data from the Ntrip server, the course base station data connecting to the course station, and you get the correction data in real time. You process here and output to some other application. So there are different versions or different possibilities are possible. I mean, different these application systems are possible. For example, you can do the real-time RTK here, or you can just log the data using a very, very low cost Pi0 that costs, this device costs about $15, $12. And you put a Gnss receiver here that's about $70, $80, maybe $100 with the antenna, and you put this $15 this device and connect the power. Then it just starts logging the data. Okay, this type of system is possible. Or you can have a receiver directly connect to your Android device. We call the RTK Droid. So this app is available. You can download from our homepage. You have to send a request to me to get the password to unzip the file. and you just connect this receiver to Android device and you can do the RTK. So it's very easy. You don't need a computer. So that's how we can make the system very low cost. Okay, and this is completely new. So I have very detailed slides for this. Okay, this is the same. Here is the one that's the receiver, small receiver. So you connect this to the tablet. Okay, and then you get the correction data. I mean the course data, basis station data from an Ntrip server that you need to have this type of a service provider in your country, in your location. So if you can get this, you can do the RTK. But please remember that this should be within the 20 kilometer or 30 kilometer of your location. But in the case of this type of very low cost system, this is a single frequency receiver. So the distance between the base and rover for RTK is a very small, about 10 kilometer to have a 20 or 30 centimeter of accuracy. So you can't do 40, 30 kilometer far away. So you need this type of correction data around you to do this type of very low cost system. Or you have to set up your own base station on the rooftop of a building, and that will be another additional thing. But we can also have a low cost dual frequency base station as well to make like for education purpose, collecting some GIS data or doing some pilot project or doing some GIS related field survey, drone mapping, and so on. And this is a screenshot of RTK Droid for setting the RTK. And this basically use the RTK Leaf inside this engine. So this is basically RTK Leaf software, which is very widely used around the world for drones and so many other applications by GNSS users. And this is quite new for Madoka PPP to give a high accuracy of 20 centimeter, 10 to 20 centimeter accuracy is possible by using a dual frequency GNSS receiver. You don't need a base station for this Madroid. You just connect the receiver to Android device, and then you get 10 to 20 centimeter accuracy after you wait for 10 to 20 minutes as well. So normally about 20 minutes is required to have a 10 to 20 centimeter of accuracy. So this is very good for a static survey. This is good for both static and kinematic, dynamic. So these are different types of products that we are making for, our sample from the university, low-cost Madoka receiver system. We have named Madwin for Windows version. If you want to connect this receiver to computer, so you can do that, but the computer is always expensive, maybe $1,000 at least. And then you have a MatPi is connecting to the Raspberry Pi device, so you can connect this receiver to Raspberry Pi. Then you reduce the cost, so you don't need this $1,000 computer. So this is just a $50 or $40 device, so you can connect to this, and then you reduce the overall cost of the whole system. So for example, in the university, so if you want to do the training or education, and if there are hundreds of students, so you can't buy 10 $5,000 receiver, so or you can't buy the computer for everybody. But this Raspberry Pi is just a $40, $50 or $60 device. So you can buy this, maybe 10 sets and 10 sets of this $200 receiver or $300 receiver and the antenna, including antenna. And then you have all 10 sets for maybe a few thousands of dollars. Yeah. So this is how we can do the system for, education or collecting the data, conducting the pilot project, or even for the real application that if the accuracy is within 1 meter accuracy is okay. These type of systems are quite good. Okay. And this is for the Android-based system using the Madoka. So again, you need this receiver and you can connect to the Android device. But for Madoka, the only problem is that this type of receiver is not yet commercially available. So this is our prototype, our device. It has a very special Madoka receiver inside. At the moment, it's not commercially available, but it will be available most probably within this year, because also Galileo, they are broadcasting providing the service in the E6 band. In the L6 and E6 is the same frequency, so they also need this type of receiver. I suppose that this year this type of a very low cost receiver will be available in the market freely. This is a low cost E6 L6 receiver, but it's not openly available at the moment. We have this some sample for our project to test the system or software and see the performance. It's quite small. You see 6 cm by 6 cm about. It's smaller than a mouse, and it can receive so many signals: L1, L2, E5, and L6, and all the systems: GPS, GLONASS, Galileo, Beidou, QZ, and SBus. Okay. And then we also need all these frequency compatible the antenna. So antenna becomes quite complex now. So you connect the antenna to this one and get high accuracy position data. So internally inside that green box, you see 2 separate receivers inside. They are combined with the splitter to the antenna and output with a single USB port, and you get all the necessary output here. So this is very compact. And this is how it looks like. For example, this is the Raspberry Pi device, Raspberry Pi 4, with the touch screen display. So we put the screen here so that you don't need a extra external monitor. So you can use the pen or your finger to scroll or touch some of these menus here and set up the parameters. There are not much settings here, so you just say to your some input parameter to select the receiver type and the data type and so on. And this is the antenna is here. So this receiver is this size. And here is an external USB memory stick. So you put the insert in the USB this port of the Raspberry, and all the data will be automatically saved in this memory device. So this is how it works. So it's very compact, and it gives you about 20 cm of accuracy. Yeah. So this is the user interface, how it looks like. So you can connect the receiver directly to your Raspberry Pi or Windows device, or you can remotely access a receiver that you have in the field or in your office from your home. So during COVID, so it's very easy to remotely access your receivers and control them. So observe the data like that. You can do that with this. And so the PPP, this technique is very good, but unfortunately you have to wait for some time. So once you put the power, the accuracy is not good. It's about a few meters. So this accuracy at this moment is maybe around 3 meters. So this is like a differential DGPS accuracy, not better than that. But to have a 10 to 20 centimeter accuracy, you have to wait about 20 minutes, 10 to 20 minutes. You have to wait, then you will get about 20 centimeter of accuracy. So this is the convergence time to solve the ambiguity and all. So the receiver needs to work for some time to give you very high accuracy. So this we have tested in a different part of in Asia. This is, I think, the data from probably from Bali, I think, yes, minus latitude, yeah. And here we show you some result, like in Tokyo, testing in Tokyo. So once we put the power on, and after some time, you have about meters of accuracy. And as time passes by, so this goes to very small error. So maybe this will give you about a 10 centimeter or better accuracy after some time. Maybe this is more than hours, okay, 2 hours or 3 hours. Okay. So it will be like this. But after 20 minutes, you will get about 20 or 20 centimeter, around 20 centimeter of accuracy. That's quite good here. And you don't need any base station. Okay. So this is probably new for many of you, because this is not available, this service is not available in other satellites. And also in Japan, we just released this product and software very recently, just a few months back. So many people probably don't know this. Okay, so these are the same things, so data from different area. I will just skip. And this is the Android version of the same Madoka. So the screenshots, I will skip this. Okay, so how the satellite sky plot the displays and provide some error related information, and also the coordinates in WGS84 lat long, and also the UTM coordinate system. So this is very useful when you are working with a local map in the Android device, because once you use Android means you're probably using some other applications in the Android, like a GIS or mapping or surveying tools and so on. So maybe UTM coordinate system is better for you rather than the latitude longitude. Also, this is easier to see the error. So if the error is already stable, like if you already have a 10 centimeter of accuracy, then probably you can see this meter, this second digit should not be fluctuate. So this 0.76, so this 6 should remain 6, so that you will have a 10 centimeter of accuracy, guaranteed 10 centimeter. And these are showing some data formats it can take directly, but since it has RTCM3, so it can take any type of receiver as long as they can output RTCM3 data format. So these are the technical specifications related issues that we need to discuss how to interpret them later. Okay, this is the same thing, different data logged at the different places and showing different type of results, but it's the same from the Madroid. Okay, we're just verifying at the different places and different, also different, little bit different way of a Madoka PPP, take the ambiguity fixing technology. So these are our prototype testing outputs. Okay. Okay, so that's all for this low cost. And then which one I should take down? So the next one, I would like to take the security, Gnss security. It will not take much long, maybe about 15 or 20 minutes, 15 minutes probably. Let me stop this one. Okay, so this presentation probably bit new for many of you, or at least some of you. So when I talk about the GPS security issues, it's not only GPS, sorry, I wrote the GPS, but this is GNSS. So basically we have 3 problems, okay? Jamming, interference, and spoofing. So these 2 you hear a lot, jamming and interference. So probably you know these issues already. And this can be either intentional or non-intentional. And there are already many research and studies exist for this type of jamming and interference issues, because it has been talked for a long time since the GPS is widely used. So there are a lot of issues related with this. And also some solutions exist, especially for very special application or military applications. Okay? But this is a very big issue as well. But spoofing is not quite common. You don't see these issues at the moment, or even if there are, you probably cannot detect. You don't detect. It's not possible to detect actually. And this is intentional. You do it intentionally. Okay? This you may be doing without knowing that you are interfering or jamming. Like, for example, you are using some devices, some electronics device that is broken or that is damaged, like you use some radio device, but it is the cable is little bit leakage or the corroded, then it transmits some leakage signal, and that may affect the GPS, like your radio antenna or your TV antenna on the rooftop of your building may be sometimes affecting the nearby other systems. Okay, but that is non-intentional. But sometimes you do the intentional jamming by using this type of jammer, like some people don't want to be tracked where they are going in their car. because now you are using the mobile phone, or the car has a car navigation system or the GPS system. So if you want to keep your privacy, some people use this type of cigarette lighter, this type of jammer. It's very cheap, maybe $40–50 of device in the internet, and many different types of systems available. And if you use this, so it will jam, of course, the receiver in your car, but it will also jam all the other system in the vicinity of this jammer. Okay? And this is very dangerous. So you will be unknowingly jamming others as well. Okay? So you may be using it intentionally or non-intentionally, but this will not jam only your device, but anybody around you will be affected. So please be careful about this type of devices. And the USA, for the last few years, this regulation has become very strict, and they have a very strong law now. So if they found you, so you have to pay a very heavy penalty, fine on that. But this spoofing is very difficult to identify or detect. Actually, it's not possible with the current signal design or architecture. So this is what now we are doing a research and lots of studies on there. We are doing it. But in general, this issue is emerged just for the last 10 years. Before that, we don't hear it much, almost zero. So, and for the last 6–7 years, there are many research coming up, many presentations and many papers coming up, but still the solution is not perfect. But we do have some solution for the QGIS. We are doing lots of work on that. And also Galileo already announced a few years back the open signal authentication, and now they are broadcasting the test signal. And this is one case that in the Black Sea, the vessels are all spoofed. So it like this is the GPS coordinate output from one of the vessel's GPS system in the ship. And Captain Red took a picture of this 44° and this flat and long. And the system says this is safe. Accuracy is within 100 meters, and that's a very standard accuracy for this type of receiver. So the captain can navigate the boat or the vessel looking at this. But the captain realized that this coordinate is a little bit different from the actual. And when he checked the coordinate, so this is in the airport here. So there's this yellow pin is the airport here. So all the boats around here, so they were saying similar coordinate, and they all point to this airport. And it's impossible that ship or vessel can be at the airport. It's impossible. So this is something wrong. So this was detected. I think this were maybe 2 years back, this data, and they thought this is a case of a spoofing. Otherwise, it's not possible. Okay, so this type of event may happen. And why this is so easy to jam, to interfere, or to spoof? Because GPS signal is extremely weak. It's so weak, like it's just transmitting about 30 watts of power. And that travels all the way down from satellite to the receiver. That's about 22,000 kilometers. So when it comes to your receiver, it's extremely weak. So it can be easily destroyed or easily controlled. Okay, so this is the reason. Very, very weak signal. It's not like a radio or TV signal. They are very, very strong. But GPS is very weak. And in terms of the spectrum, the power spectrum, we call it the power spectrum. If you see here, this is the noise, thermal noise, means any electronic device like a mobile phone or any device, if you put the power on, by default, you will have a natural noise or the thermal noise. So it will depend on the temperature. But by default, for 2 megahertz bandwidth, which is similar to GPS at the GPS frequency, you will have this level of noise. Okay, so you put any device, you will have this level of noise. So to work any communication or any radio signal, this signal power must be above the noise. Otherwise, it doesn't work because now it's hidden everything inside the noise floor. Okay, so you can't see, you can't measure this signal. But GPS is very interesting that GPS is a CDMA modulation, and it's the purpose of doing this is to hide all the signal inside the noise. So once you modulate this signal in the satellite before transmit, So they are all hidden inside the noise, and it comes to the receiver as a noise. So you really cannot measure using any type of RF signal, radio signal measurement device, because it's inside the noise. And if you don't know what are the PRN codes or the codes that are used to generate the GPS signal, you cannot detect, you cannot read the signal at all. So this is the secrecy of the signal design, because GPS basically emerged from the military use to keep everything secret. So they want to hide everything inside the noise. So even if you receive this GPS signal, it just appears like a noise. So that's the purpose. And this is the P code for the military. So everything below the noise. But now for civilian, this P code, the PRN code, all this information are published. So we know how these signals are made. Then what we can do is in the receiver, we can demodulate. And once we demodulate, so this signal comes above the noise. Then we can read and detect. But still the power is very, very weak. So it can be easily jammed, easily interfere, or easily spoofed with a very small or cheap device. So that's the disadvantage of this signal. I will skip this one. This is just showing that if you put a very small power jammer, how long, how many, like this is a 10, 0 is 1 meter, 10 meter, 100 meter, or 1 kilometer. So to jam to up to 1 kilometer, how much power you should transmit. And this is minus 64 is legally in Japan, you can transmit this much of power by a jammer. So if you do that, you will jam everything up to 1 kilometer of radius. Okay? So that means you should not transmit any signal that will jam the GPS, although by regulation it is okay. And it also says that you should not transmit anything that will cause interference or jamming to others. Okay? So there are two things, the power level you can transmit, and then you should not harm others. Okay? Then you cannot transmit anything. So if you do this type of jamming and interference, so what it will affect is like if there are no such jamming or interference, so the signal is very clean and the receiver has a very easy signal processing. So it takes less power and less memory to do this. So your battery consumption is smaller. But if it is more jamming or interference or noise coming, then the battery consumption will be very high, power consumption will be very high. And the mobile phone designers or the device makers, their concern is to how to minimize the consumption of the battery, because the mobile phones are designed or the specifications, there are some requirements that in case of emergency, like if there's a huge emergency like or disaster like earthquake, like people buried in the buildings, so people can they can still live without any food or drink for 3 days, 72 hours without anything. So that means your mobile phone should work at least to get the emergency signal or to send some signal from your device. So the expected running life of the battery is 72 hours, okay, in such emergency cases. So it's just sending some signals to the cell tower so that the telecom company can know where you are. That's the purpose, to minimize the power consumption. But if there's a lot of noise coming from these jammers and interference, the receiver maybe need to work hard and it takes more power. So instead of 72 hours, your battery life will be drained out within maybe 24 hours or less. So there should not be noise actually, which are unwanted. Okay? So that's the very important design spec from the mobile phone companies. So we don't know much of these things, so probably you are not much aware of these things, but these are what they consider. And that's the reason they don't want to put so many unnecessary things in the mobile phones unless it's a very specific requirement. Okay. Now, these are some experiments we did when we put more noise, what will happen? Like this is one of the receivers from Septentrio. And this is a normal case. We can see this type of spectrum in the receiver. And when we inject more noise, so this is the noise. So this is how the GPS signal looks like. So this is the signal that appears in the antenna. Okay. So we just convert from the antenna RF signal to digital, and we plot the radio signal, the GPS signal. So it's like a noise. You can't see anything here. And the power spectrum is like this. So we see something. This is the GPS L5 and L1. Sorry, L1. We see a little bit of signal coming here, and we inject some noise. Then this pattern is now damaged. Okay. Now with this, you cannot get the position data, and we see a very strong signal coming up. So once we see this, we think this is either jam or strongly affected by interference. And this type of position data, even if you get, you should never trust. This will be very bad position data or no position data at all. The GPS will not work at all. So this is the interference issues. And to protect such things, so this is all controlled globally by ITU. So ITU has some standards and regulations. So how much satellite, how much power they can transmit, and what frequencies they can use for globally for GPS, for other radio communication, and even for GPS there are different bands, L1, L2, L5, and L6. So in each band, so how much power you can do. So all these are controlled from ITU by ITU. And with these references, data or values as a reference, then every country has their own radio regulation. And for example, this is for Japanese radio regulation. Now, if I want to transmit some radio signal, I must comply within this regulation guideline. For example, now for my research purpose, I want to do some new signal testing. Then at this frequency, which is GPS 1.5 gigahertz, so my transmit power must be less than this power density, 35 microvolt per meter. Okay? So must be less than this. If I transmit more than this will affect other systems. So this is what it's telling. So if I am transmitting smaller power, then it will not have an impact to other systems. So this is the regulation saying. Okay? So every country, they have this type of regulation. So you can check with your country and see whether it meets or not. When you buy a receiver, some receivers, they come up with Bluetooth and Wi-Fi, and also sometimes a radio. So that radio may be in the 900 megahertz or 700 megahertz or 400 megahertz, different frequencies. So you have to check whether this radio, which is included in the GPS receiver, complies with your country's radio regulation or not. So you need to ask the radio regulation authority in your country whether you can import that GPS receiver that has a radio of 435 megahertz and the transmit power is say maybe 1 watt. Maybe they say no, 1 watt is too much. You should have only 100 milliwatt. Okay? Or for the Wi-Fi and Bluetooth, it has a different regulation. So please check if you're buying. And also the manufacturers, they provide this data. If you say you are buying a receiver for your country, they will tell you, okay, this receiver you can use, but another receiver cannot use because it has a different type of frequency. Okay, so you can ask both the manufacturer, the company, and also your radio regulation. This is very important when you buy the receiver. If you buy without knowing this, and once it comes to the customs, then you will be in trouble. Okay? And basically the RTK capable receiver, they will have some of these radios sometimes combined with the receiver, or they may come separately together to send you the data in the real time from the base to the rover. And this is the spoofing issues. So I don't go to detail, just show you some slides and give a definition what is spoofing. So this is spoofing is just to lie the position data. For example, now I'm in Tokyo, but I can lie to my GPS receiver or GPS of my mobile phone to show that I'm in Hawaii. And this is very easy. I just need to buy a signal generator, GPS signal generator, or we call the spoofer. It's just a few $100. Software is available, and we can program, and I can program this device to output the signal so that my receiver will show I'm in Hawaii. So everything will change to Hawaii, but this receiver will not complain at all. Okay. So this is what we call the spoofing. This is to falsify your location data, your GPS signal. By falsifying the GPS signal, you change the location data, and the receiver doesn't complain at all. So we did a lot of tests on this. Now we are developing the anti-spoofing solution. So how to protect from such attacks is our main work. And this idea, or you can watch this movie, Tomorrow Never Dies, in the release in 1995 or 6. So this is the whole story about I think the GPS is spoofing. They don't say the GPS is spoofing, but this is how they change the coordinate data, and all the stories begin here. So what we want to tell you that, so whenever you get the position data in the mobile phone or in your receiver, so can you trust or not? Okay. Today, yes, we can trust, but when you have all these applications, ITS and automated driving systems and all, so if somebody changes your coordinate data, the consequences may be very dangerous, because now the GPS, your system is showing that you are driving on this lane, and suddenly the system will show you are on different lane. And if it is autonomous driving, so it will take a different decision to go back to the previous lane, but the car is already there. So it will move to some other different lane, and it may cause an accident. Okay? So this is very dangerous. So this is a sort of attack now. So to prevent this, we need to modify some of the signal, not to modify the signal, we can't do that because signals are already broadcasted, but we can add some additional information to the signal to tell that this signal coming to your receiver is spoof-free signal. So this is what we are doing. Okay. So you can trust, but we need some sort of mechanism to verify whether this signal is actually coming from the satellite or not. Okay, this is what we need to do. And so this is one example. So probably you can see now this car is actually in the parking area. So I did some simulation to show that, no, this car is actually moving around the road. Okay, now when there's a traffic light, it stops and then moves again. And you see all the satellites, speed, time, everything normal. Okay, you don't see anything funny, but actually the car is never driving. It's always in the parking area. Okay, so this type of cheating or this type of false data is possible. We did a similar demo in Indonesia for this illegal fishing, like the fishing boats. They jam their GPS receiver so that the control authority don't know where are the boats. Okay, now jamming we can detect because you also jamming others. So if your GPS receiver also jam, you know something is wrong. But if you do the spoofing, you really don't know whether somebody is sending the false data or not. So here I put the two figures. So this is we did some spoof test of the boats, and one of them is wrong. One of them is right. So we really don't know which one is wrong or right looking at this data, GPS data, because this is in the port area, near the port area. So the speed is very slow. It's moving slowly from here. This is following a ferry route from one island to another island because it's a ferry route. So it follows the route of the ferry. It's going at a high speed. Okay? So you think both of them are correct. Okay? But this one is not the correct data, but we just spoofed it to show that actually we are here, but we showed that we are going this direction from one island to another island. And if the authority see this GPS data, the authority trusts that you are right. You are going from one island to another island, but actually we are not. We are still here. Okay? So this is what spoofing is. So you cheat the location data, and this can be done rather easily. Okay? So to protect from spoofing is very, very challenging, and it's very difficult. You can't detect that this is a spoof data at the moment. It's impossible. Okay, so that's all for these two, and now I have the last one. And before going to the last one, So I want to see whether there are questions, and then we can let me have a few minutes of break, and then we can proceed for the last one. Let me see there are questions or not. Yeah, there's one very interesting comment. First case you gave for spoofing looks like a spoofing to enforce no drone flight zone or special use airspace. This could prevent to launch drones around airports, since geofencing in drones would prevent them to launch when they find themselves near runway. Yes. Yeah, this is one of the applications. Actually, we can also do the spoofing to protect this type of geofencing. But on the other hand, so we can also spoof the drones to break their geofencing zone, because I think nowadays the drones have some geofencing zones already defined in the database. So if you try to fly the drone near to the airport, then it will not go there, because the drone will think this is the protected zone or no fly zone. So the drone will not fly there, it will come back. But you can break that by spoofing the drone's receiver, but also you can do the other way around. It's not in the airport zone, but you can make it as the airport so that the drone will not fly that zone, even if it's not an airport. So we can do very tricky things with all these things to control the drones or even the ships. So this is possible. Yeah. Okay, we'll go to the last part. And before moving that, I would like to announce you that probably you have received email from ICZ, or you will receive to send the feedback of this training today. So we'd like to have your evaluation, how this training is whether this is effective for you, interesting for you, and how we can improve. So please send your comments to the link that will be provided by ICZ later. We do need those type of comments and suggestions from you so that we can improve. And this is the first time we are doing online training, so we know that online training is not effective to the level that we expect or you expect, because we can't have any hands-on exercise or like that, and it's rather difficult. So it's just a one-way talk at the moment. So we can't have very much interactive discussion as well, due to various other factors, time zone and time limitation of the time, and management of the resources and so on. But nevertheless, so if this situation continues, we need to do something similar like this, and so we need your comments or recommendations on that. Okay, so let me share another slide, and okay, so I think this is one very interesting topic for today, and I don't know how many of you deals with these type of things, and sometimes we don't care, but sometimes it's quite difficult as well. Just a minute. Okay, so let me start because it will take more time. So basically, when you want to buy a receiver, so you will ask some company to provide some document, and the company will ask you what type of receiver you need. So you will say, okay, I want to use the receiver for GIS data collection or surveying or mapping, or maybe for transport studies and so on. And then you will say, so I have this way of data collection I want to put on a car and log the data all the time whenever I drive the car, so on. And then also you will say maybe this is a real-time observation, or you will be also doing some post-processing, real-time and post-processing both, but you will not be doing the maybe not the real-time correction, but maybe only post-processing correction, or you may be doing the real-time correction like RTK and doing also post-processing for error analysis and so on. So there may be different applications that you will be doing, or you just want to buy a receiver, maybe 10 receiver for education or training purpose, or just to do some pilot project. There may be different requirements. So the first thing is we have to see the specification or the technical spec. You can check any GNSS receiver's technical specification. They varies a lot depending upon the type of the receiver, high end or the low cost, or some receivers they will say, okay, it's a 10-meter accuracy and output 1 Hz data, and it can give you NMA and it's $100. That's all, maybe few lines, but some are very detailed. But anyway, nevertheless, so you will see in detail, you may be seeing something like this. Like one is GNSS related, the signal related itself, and this part is not related with the signal, nothing to do with the signal. Okay, here is a GNSS related, for example, GNSS signal capabilities. Okay, what type of signal it can receive. I have detailed slides later. So, and also what type of antenna you can use with this, or what type of antenna is required for this receiver, and what type of special signal processing techniques it has in the receiver that's provided by these companies who manufacture the receiver, and what type of input and output data formats it can take or give, like NMA, RTCM, and BINEX, RINEX, and so on. And positioning performance, whether it can do DGPS, RTK, PPP, and so on. Of course, SPS is the minimum you get. So then in addition, you will have DGPS, RTK, PPP, and so on. And what type of communication interfaces it has, whether you can use a mobile phone to connect, whether you have a Wi-Fi, Bluetooth, internet, and so on. And data logging, whether you can log the data within the receiver, or whether you need a separate computer to log the data. Okay, this is very, very important. And if it can, so how much data you can log? Can you log for 1 day? Can you log for 1 month? Can you log for 1 year? What's the data size volume you can log? User interface, so what type of interface you have? Can you connect through the internet? Do you have a display panel on the receiver? What type of GUI you have? This graphics user interface, what type of controls you can do this? Can you set some parameters from this or not? Or you can just see some satellite values. So all these type of things are the part of the specification. Some are critical, some are not very relevant. And besides this, so some receivers are made for specific applications. Yeah? Maybe they will say, okay, this receiver is for the geodetic survey. Very high-end survey, receiver, or this may be for the normal application like IoT, LBS, so the accuracy is not good, and it's very simple, very cheap, and easy to use. Okay, or some may be the very specific, like the ionospheric scintillation monitoring, is very special receiver. Okay. On the physical properties, so what is the weight and the size and so on. Environmental properties means whether it can withstand some like a humidity or temperature or snow, like you want to put the receiver, the antenna, not the receiver, but also the receiver, the outside. So when you bring the receiver in and out in a very big difference of temperature, so you will have this humidity problem. So whether this receiver still works or not, or if the temperature goes down below -10, -20, or goes up to be above 40, does it still work? For example, you put a receiver in the car and you park the car in a parking area for 4 hours. So in a very hot country in the summer, so if the outside temperature is 35 or 40, the temperature inside the car may go up to 60 or above for 3-4 hours in the sunlight. So it's very, very hot inside. So does the receiver still withstand that much of temperature or not? Okay, these are some environmental and electrical properties. So what type of inputs power supply it requires, whether this is a DC supply, AC supply, whether it has a battery inside, and how long it lasts, how it can be charged, and all these things, and security. So whether there is some security restrictions, like you need to put some password to access it and all. And whether this complies with your country's regulation. I said that if you buy a receiver that has a built-in Wi-Fi, Bluetooth and all, so what are the regulations and with your country, whether it meets or not. And also some countries has a disposable regulatory and some other PCB, the lead-free, the requirements. And in Europe, this some regulations are very, very complex and very strict. Like if you want to dispose the receiver, so it must have all these the disposable guidelines met by the product. So some very minor things, but it's makes the import or the export very restricted. Now we go to the details. So GNSS, this is about the signal capabilities. So first thing is you have to know whether you need all the satellites or not. But recently, so many chip makers, they already included the capabilities for this. So without all, now if you say just the GPS and Galileo, maybe it's even difficult to buy if you're trying to buy the new modern receiver. I mean the new receiver. Some old receivers, they are of course GPS Galileo, but for the little bit of a high accuracy and good receiver, I think they are already multi-GNSS receiver. Okay. But here is a big difference. So here probably you have everything already, whether you want or not, but the manufacturer or the companies who sell, they control which signal to receive by like a license or the cost. If you pay all the license or the price for everything, probably you can receive all, but probably you don't need it. So they have some sort of a sales plan to include the minimum required signal and everything on top of that, then you pay and they charge you more. Okay. Sorry. And the price goes up as you choose more signals. Sorry, sorry. So the price goes up. For example, now probably GPS L1, L2, probably the minimum requirement. And if you say I want L2C or you want L5, then you pay more. Okay. For GLONASS, so L1, L2 is common. And now GLONASS is also transmitting new signal in the CDMA band, I mean the modulation signal, and L3 band. So if you say this, probably the receivers are not very widely available. So probably you really need to find this receiver that can receive this signal and pay more. And for Galileo, L1, or this should be E1, E1 and E5. And if you go to sorry, is this okay, my presentation? It seems that there's some problem.
It's okay, Dinesh.
Okay.
At least on our side, we can see it
Anyway,
clearly. Thank you.
Okay. So depending upon the signals you want to use in your receiver, the price goes up. Okay. So make sure which signals you need. If you don't know, you really need to discuss, and depending on your application and purpose. So the more you put, the more you pay. And then antenna type. So what type of antenna you need? Okay. For some very high accuracy survey, so probably you need the all system and some multiple signals. Okay. So again, so this is the antenna will be decided by these signals, okay, and these systems. So systems and signals will decide the antenna type. But sometimes when you buy the antenna, like you buy the receiver only L1 and L2 and L1 and L2, but the price of antenna that is only L1, L2 or L1, L2, L5 may be sometimes similar. Okay? So that you have to see. So if you pay a little bit more, and if you can get L5, so it's better to purchase L5 because that will save your future the investment for the future when you upgrade your receiver. And the installation of antenna is very, very costly. Okay? So we are not considering the antenna installation cost here because the antenna may be just $3,000 or $2,000 or $1,000. But to install $2,000 or $1,000 antenna, you may probably have to spend another few $1,000s. Okay? Power supply to the antenna and the mast and all the support and the environment and all. So that costs a lot. So when you set up the antenna, if it is for the high end, so please consider a good antenna and with all the necessary things in the beginning. That will save your investment for future upgrades. And the manufacturers, they will tell you what type of antenna you need depending upon the receiver type. So all these parameters will be related to the receiver type. So you don't have much choice on this. So if you decide the receiver, then your antenna will be decided, and you should use the antenna that is recommended by the receiver manufacturer. So don't use the antenna that is not recommended by the manufacturer because they will have a different voltage, like a power supply. They will have a different gain, the low noise amp in the antenna inside. So it will not match. And if you have a long cable from the antenna to the receiver, so your receiver may work properly. So the best thing is to use the antenna recommended by the manufacturer. And some manufacturers, they also sell the antenna and the receiver together, but some manufacturers, they sell separately. But mostly they combine together for the high-end receivers. And then the one very important thing is whether you need a choke ring or not. Okay, so this choke ring is probably, basically, yes, it's good for the area where you have like a heavy snow and all, and also, I mean not the choke ring, what you call the cover. Okay? But this choke ring will help you to reduce some multipath coming to the signal. Okay? So again, you have to pay maybe at least $1,000 or more for the choke ring. And then you have the cover for that choke ring, different shapes. So if your area is a heavy snow, so you will select the cover that's more like a cone, so that the snow will not stay above the antenna. So different types of things you have to consider. And when you go to the very high accuracy, and then also you will be looking for the calibrated antenna, and they provide you some antenna, this phase center offset and phase center variation data for like antenna. Okay, so some of this high grade survey grade GPS GNSS antenna, they have this database data available from the manufacturer, and this is necessary to do the PPP or RTK with a very high accuracy, because you are using an antenna that's about maybe 5 centimeter in diameter, okay, or quite big. So say 5 centimeter in diameter. So using an antenna that is 5 centimeter in radius, okay, 5 centimeter in radius, using this 10 centimeter diameter antenna, you are trying to compute the accuracy of 1 centimeter or 2 centimeter. So how can you compute how can you get 2 centimeter accuracy with a scale that can only measure 5 or 10 centimeter? Normally, it's not possible. Okay? But in the GPS, so if you have a PCO or PCB, so you can know exactly where are these electrical signal, the waves entering to the antenna. Okay, so that's a phase center offset. So the center of the antenna may not be your exact center where the electrical signals enter into the antenna. It may be a little bit different. It may be sometimes even a few centimeters off from the center. For L1 and L2 may be different phase center value, L5 may be different, and so on. So these data are measured and calibrated and available for survey grade antenna. And also the satellites are moving, so its elevation and azimuth is changing with respect to time. So this PCO is changing. Okay, that is the phase center variation, PCV. So with respect to the elevation and azimuth, your PCO is changing a little bit, and these data are available. So if you are buying this high accuracy antenna, you get this data from the makers. So get it, and then you set these parameters in your software. And the software, you use these values to provide you the best possible accuracy for your observation. Yeah. So that's why the survey grade or geodetic receiver, so it can give you the centimeter or few millimeters of accuracy. Okay, removing all these error, offsets, bias, and so on. So we need a very detailed data like that. And some receiver manufacturers, they have their own technologies. So proprietary means these are the receiver manufacturers' technologies, their own, not the standard. I mean the common methods. So they may have their own multipath elimination technologies like Trimble, Novatel, Septentrio, Java. They have their own way of removing the or minimizing the multipath that's coming to the signal. So they have a different names, different brands, and so on. And some receivers, they also have a weak signal tracking technologies to get position data even from a very weak signal, although the accuracy may be bad. And some of them, like for the receivers in the mobile phone, they have a Gnss capability to give you some position data, even if you are in a little bit different environment, like semi-indoor location, like in the building, if you have glass walls and all. So it can still give you a position data with some assistance input from outside. Or RAM is this is detecting or checking whether the position data is good quality or not by looking at a certain this is the receiver autonomous integrity monitoring, okay, to check whether the pseudo range, care phase, all these signal, we call the signal health or the sanity check of the signal. Whether the signal is suddenly changing, like during the spoofing and all, if the pseudo range changes suddenly, if the Doppler changes suddenly, normally it doesn't, but sometimes it jumps to a very large value or very small value, and then we see something is wrong with this signal. So this type of some capabilities will be there in some receivers, and some receivers, they have anti-jamming capabilities to some extent. It's not always possible, but there exist. Okay? And this is completely new. So at the moment, no receivers have this. There's no receivers, but we are developing our own prototype for this. And Galileo is now coming with some models already they announced. So probably some Galileo receivers, capable receivers from Europe. And we have our own prototypes. So we are using many different types of receiver, commercial receiver for this. So we are modifying the software for that. So this is available as a test or prototype, but not in the commercial. And some receivers now, they have this spectrum monitoring like U-Blocks, Septentrio, Trimble, and I think Java. They all have this type of noise monitoring screen to see whether the signal quality is good or bad. So it depends whether you need these type of things or not. Okay, sometimes they charge, sometimes it's free. And this is very important, output data formats, input and output. So you have to check what type of outputs or inputs it can provide, like RTCM2, RTCM3. This is, I think, the minimum requirement if you are If you want to do the real time, this is necessary for real time RTK or PPP or other things. So these are necessary. And the receiver will have a proprietary formats as well to send their own binary format data. And then observation data to log the GPS pseudo-range care phase data to create the RINEX or BINEX, so on. And it can be either RTCM or BINEX. Okay. And the position output data from the receiver. So NMA is an industry standard. So I think almost all the receivers, they have it. So you don't have to pay any extra for that. But some of these, maybe some receiver manufacturer, they charge extra. If you say, I want RTCM3, okay, you pay maybe some extra cost on that, maybe a few $100s on that. And also the output rate. So what output you want to have. So basically, many GPS receiver, they provide at 1 Hertz. This is a sort of a standard. But some receiver, they provide very fast output, 10 Hertz, so 10 outputs in 1 second, or 100 outputs in 1 second. This is very fast, high rate, but this high rate data will be a bit noisy as well. But nevertheless, it may be good for some other integration with the IMU sensors, because IMUs, they work at a very high data rate, around 50 Hertz or 100 Hertz. So if you also have a GPS data coming at 100 Hertz and the IMU also at 100 Hertz, so it's much easier to do all this integration and interpolation between two different types of systems. And basically, like systems that use tight coupling. So now we are talking with new terminologies like a loose coupling or tight coupling in the IMU, inertial measurement unit device, and the GPS. So they prefer this high rate data output rate. But if you are using the loose coupling, probably you can't, it doesn't make any sense. Even if you have 100 Hertz data output rate, it will be quite noisy. Maybe 10 Hertz or 1 Hertz is okay. But the higher rate is preferred. But again, this high rate means high memory, high CPU in the receiver, so you have to pay extra. Probably the receiver will charge more for this output rather than this one, and it's quite complex as well to maintain the accuracy and all performance at this high rate. Okay? It takes more power and all. And the timing, so some receivers, they output the 1 PPS pulse to integrate your GPS with other timing systems. Like I told you that GPS can be used also for timing applications in the communications, internet, and finance. So this is what they use, the 1 PPS output from those receivers to exactly synchronize the clock of other systems. And some receivers, they also have a clock of 10 megahertz output or input. Means if you want to synchronize different types of systems with your GPS, or if you want to see the clock accuracy of your receiver itself for a very special application, so you need a receiver that can also take this 10 megahertz input. Okay, but also the receiver will also have a 10 megahertz output to send this signal to other systems, to control other systems. And event trigger means like you are observing every day continuously for 365 days. But sometimes you want to observe only in certain cases. For example, you can set if this satellite goes below max angle or elevation of 15 degrees, start logging the data. So that means when the satellite goes below the value you set, it will trigger the output. So you get the output. So you don't get other output. So you get the output only when some incident or some event happens. So this is what it does. Okay. And then support to other sensors means like if you look at the course stations, so they have some high-end systems. They have this meteorology, temperature, humidity data recording, and the tilt sensor. So this data also embedded into your other GPS data, and they can support this one. This tilt sensors very important for this millimeter level of observation, because you have antenna on mast or some the base or the pole, and due to the temperature variation, the antenna mast or some if it's a metal structure, so it may change. Yeah. that minor this tilt or the change in the platform or the mast, so it can be measured using this type of tilt sensors. Now this is the most important part. So you will be always interested about accuracy. Okay, and there may be standard positioning accuracy, DGPS accuracy, RTK, NRTK, PPP, so many of the calculation techniques. And this is one example how a manufacturer has listed here. This I took from a Trimble because it's quite detail. And you see here DGPS, code differential GNSS positioning. And if you look at their catalog or their technical spec, you see all these 5, 6, the small letters. So they write this and they have a detailed comments in this small letter, and you have to read this, okay? Because they are giving very important information here. And it says the horizontal accuracy is 0.25 meters plus 1 ppm, and this is RMS value. Okay, so before we discuss whether this is RMS, CP, 2D RMS or ACP and so on, now they said this is the RMS. So this is the RMS means 1 sigma. Okay, this means this receiver will give you in the DGPS code differential observation technique horizontal accuracy of 0.25 meters plus 1 ppm, and this accuracy can be guaranteed for 1 sigma, means 66.7, I think. So in the if you observe 100 times, so 66 times you can receive this level of accuracy, but 34 times they don't guarantee. It may be anything. It may be 3 meters, it may be 2 meters, it may be 0.5, it may be even 10 meters. So we don't know. Okay, you have to log the data and see how it spreads, okay, how it varies. So this is what it's saying. Now this 1 ppm, the meaning of this 1 ppm is I have to show you another slide. Okay, so let me just tell you. For all these differential GPS and RTK, we need a base and a rover. Okay, now this base and rover, we have some distance. So if this distance is a 10 kilometer, how much error will be there? So this 1 ppm is telling you the error due to the base length. Okay, so this is that parameter. This you will have, even if you have a 0 base length, even if you have a base and rover very near. So this is a fixed error you have. Then the variable error is based on the base length, okay, the distance between the base station and the rover. And this 1 ppm is 1 parts per million. So I think I have a slide here to explain. Oh, okay, this one. So this 1 ppm is like this. Okay, now you have this for DGPS or RTK, differential correction technique. So you have a fixed error of say 2 centimeter. And y ppm, 1 ppm. So this 1 ppm means 1 centimeter of error in 1 million centimeter distance between the base and the rover. This is how we read. Okay, okay, 1 parts per million. So if you change the unit from centimeter to kilometer, so this means, so I changed to this 1 ppm, I changed to 1 centimeter. So then you will have 1 centimeter of error every 10 kilometer of distance between the base and the rover. Okay, that means if your base and rover are separated by 10 kilometer, then you will have a 1 centimeter. So that means your total error will be 3 centimeter in this case. Okay, so now let me see, this is 1 centimeter for 10 kilometer. So this means you will have 1 centimeter of error when they are separated by 10 kilometer. Okay, so your total error will be 1.25, 0.25 meters. So this is 25 meters plus 1 cell. So you will have a 26 centimeters of error. That is RMS. This is what it's saying, okay, for DGPS. So let's go to RTK. So here it is interesting now. Now it's saying that real-time kinematic, if the base length, that's the distance between base and rover, is less than 30, they guarantee an accuracy of 8 millimeter plus 1 ppm. So what accuracy do you expect if your base length is 10 kilometer? Okay, so this is 8 millimeter, and for 10 kilometer, this is 1 ppm. So already we saw that for 1 ppm means 1 centimeter per for 10 kilometer. So if it is separated by 10 kilometer, you will have a 1 centimeter of error. That means the error due to this base length is already 10 millimeter. Okay, so 10 plus 8 is 18 millimeter. So you will have an error of 18 millimeter actually. When they are separated by 10 kilometer, you will never get 8 millimeter of accuracy. It's impossible. Okay, because they are saying, the manufacturer is saying, this is the data from their test, and they gave you the most, the best possible data here, because the manufacturers don't want to show that their receiver is bad. So this is the best possible observation for the RMS 1 sigma, and that's 18 centimeter of 18 millimeter of accuracy for a base length of 10 kilometer. If the base length is less than 10 kilometer, of course, this is better. So this is maybe for very short base length. Okay, very, very small base length. So you have to be careful. So many people, they buy the receiver and they do the survey and they say, oh, I never get this 1 centimeter accuracy, because you said this is 8 millimeter, let's say 1 centimeter, but people complain it never gives. But then they will say, please see this figure, 1 ppm, and also we said RMS, and then they will ask you what are you observing and what are you calculating, whether this is 1 RMS, 2D RMS, CP, and how did you observe, and so it's very, very complex to calculate these errors. But these are the guidelines. Okay, you will never have 8 millimeter of accuracy. You always need to look at this figure, what is 1 ppm means, and what is this, and how to interpret this, and depending upon your baseline. Now you go to little bit other, and they have a network RTK. This is another correction data. So if you use a network RTK, it's better. Okay, so this is what it says. Then the accuracy is not 1 ppm. This is 0.5 ppm. Okay? Because in the case of network RTK, your base length is smaller than in the case of RTK. Okay, so that's the reason they put 0.5 ppm, because that probably is possible in their system. So please use this type of guideline. And okay, so probably all of these are for static observation. Okay, so this is very important figures, ppm, and how to interpret RMS or like that. And then you probably need some communication ports here. So what type of ports are available? Serial port, USB, Ethernet. So this may be important for some other applications. If you have a USB ports, maybe it's easier to log the data or copy the data, but sometimes it's disadvantageous because of the security reasons. So probably you don't like it in some cases. Maybe only serial port or Ethernet, also serial port, I don't know. Maybe this will be more secure. And Wi-Fi, so if you have a Wi-Fi, Bluetooth, again, you have to see whether your country regulation meets this or not. And the data logging capacity, so this is very important, whether you can log the data internally or not. So of course, high grade, these survey grade receivers, they all have this type of capacity. The low cost receiver, they probably don't have it. Okay, so you have to log outside of the receiver. And also in the high grade, so if you can log the data, so how big that can be, one single file, and whether it's only for 34 hours, whether you can log for 30 days, 1 month, 1 year, and so on. Because sometimes you put the receiver in a very, very remote area where you can't go even once a month. So the receiver must be able to log the data as you want for a very, very long duration, maybe at least for 3 months or 6 months like that. There are so many research going in a very difficult terrain in Antarctica and so on, where you can't travel, so you have to keep the receiver there for long duration, 3 months and 6 months, and every 3 and 6 months you go there and get the data download. Okay, so it is very, very important depending upon how your working environment is. And this is another very important parameter, physical and environmental. So physical, maybe size and weight, maybe not very critical, but this temperature is very, very critical if you are going for a very high accuracy receiver system. Because if you look at the receivers, they have this -20 to +40 or -20 to +65. -40 to 65, -40 to 80. So if you want to use a receiver inside the car, probably you have to look this one, okay? At least +80. Okay, so this one is very important, and sometimes they go up to -40 to 125. And sometimes there are some very highly industrial things, so maybe -60 to +125, but that will be quite expensive as well. So this means some impact on the price. So it affects the price as a whole. So it will be completely different price scale when you go here. Okay? And humidity and shock. Okay, so you probably in a harsh environment, in the rough use, so you are doing the mining and all these type of applications. So even if the receiver falls from the 1 meter, so whether it should be okay or not, if you have that type of requirement, so you tell in your specification that this must be at least 1 meter drop test safe. Okay? So even if it falls to a concrete floor from a height of 1 meter, it should work. If that's your requirement, then that's another price to you. But if it doesn't, so it's a completely different story. And vibration is very critical if you want to put on some machines, tractors or vehicles. Okay, so it's a very, very important. Even for the low-cost receiver, some low-cost receiver doesn't work when you put on your body and if you are running or jumping. Okay, normal walking is okay, but if you start jumping or running, I mean the very brisk running, so you have lots of vibration on that, and some receiver doesn't work. Okay? So you need to make sure that the receiver works properly with your motion. And IP certification, so waterproof and all, so dustproof, waterproof, and so on. So what level of this protection you want, so you can specify. And user interface, so what type of interface you want, whether you want just a SkyPlot display on that, CN0 and so on, or whether you want all these displays and LEDs blinking, if there's some error, giving you error, if RTK is not fixed, give you some LED light on, off, and language support. So when you buy the receiver from some companies, so some companies, they have a different product for domestic use and for the foreign use. So if you buy a domestic product, maybe the language may not support what you're looking for. But if you buy a Japanese product, so it may be only Japanese language and it may not have an English interface. So you have to make sure that you have a language interface that you understand. Okay. This is, I think, antenna I already included here in the previous slide, so not relevant here. And electrical properties, so this is very important as well. So what type of power supply the receiver requires, whether it works from all the voltage, 5 volt to variable voltage, or whether it is only limited to 12 volt or 24 volt and so on. So better to have a very variable power supply input so that you can use anywhere. Means car, normally they have a 12 volt, or the trucks probably 24 volts. So maybe you have to go not 18, I think this should be 28. So this type of variable input sources is better. But if your use application is limited only in the room, in the lab, so probably just the AC power supply is okay, and that adapter will give you the necessary power input to the receiver. Okay? And whether the receiver has an internal battery or not. So this is also depends on your application. If it is coarse, so it's better to have a internal battery because of power supply failures, city supply failures. So your internal battery will protect from losing the data or logging the data. So this is very important. But in some cases, like if you are flying frequently and you are taking the receiver, maybe internal chargeable battery, maybe a big trouble, lithium ion you cannot carry in the aircraft easily. You need a very special packaging and the permission for that, so it may be troublesome. So don't buy this internal battery receiver. And what are other? And then this is the important part, regulatory and compliances. So see whether it meets the some FCC like in the US, but Europe, they have the European regulation, and in other Asian countries they have their own. But this FCC Part 15 is very widely quoted and used. So this means that if you put the device some power, it emits some noise or signals, and that it doesn't interfere with other devices. This is what it's saying. So make sure it has, but mostly, so if you check at the specs, so they already have. But if you are going for a very low cost devices that you really don't know, probably they don't have any of these clearances because it requires a lot of testing, and so this type of certification is quite difficult for a very low cost system. So this itself costs a lot of money for them, so they don't go for such clearance. Okay. And then the country-based radio regulation, the Wi-Fi, Bluetooth, if it has any type of this, so make sure it works. And battery-related problems and the lead-free. So some countries, they are very specific on this. So make sure whether you can import such devices to your country. And this is just a price guideline. So then finally you will come, okay, I want all these specs, but what is the price then? Then probably you will end up with a $10,000 receiver or maybe $5,000 receiver, but you have only $1,000 receiver amount budget to buy. So then you have to decide what application you are going to use. And this is very, very important requirement, the accuracy. So where are you now? So whether you need 3 to 10 and 30 to 100 or above 10 to 20, okay? This is a very critical factor, this accuracy, 30 to 100 or better than 30. So here is a big margin. So the technology here is now becomes quite different. And if you are going for like standard accuracy, so this is probably even few dollars to maybe 10, 20, less than $100. But as you go up, it goes up. So you need to take so many factors into account and decide which one is best suitable. But these figures are just for comparison purpose, so I don't have the exact figure for that. There are so many brands, and also there are receivers manufacturers sold by the original chip makers like Trimble, Novatel, Jabbar, Septentrio, and Ublox, and Lorraine, and the Broadcom for all these things. So different types of. And there's another category they call the OEM, or original equipment manufacturers. They also sell the GPS receiver. They have their own brand name, but inside their box, inside their brand name, they have a chipset or module from another maker. They may be having Trimble, or they may be having Novatel, they may be having a Septentrio, they may be having a Jabbar inside the engine, but they will have another brand name. Okay, so they are the OEM. So the price of the OEM and the price of the original may be quite different, because OEM manufacturers, they only use the engine inside. All the other interfaces, battery and so many other GUIs and all, they customize as per their customers' requirement and their target application or their intended market targets. So the price varies a lot depending upon the market and also the receiver manufacturers. And also you need to know whether those receiver manufacturers are OEM makers or the original makers. So these all differ. So normally the original maker, so the price may be a little bit above, but the OEM may be a little bit lower side. But it's up to the users which one to buy. Okay. But one thing which is very important for course, because course, all these reference stations are designed to work for 10, 20 years of lifespan, and they normally put outside of the room. So imagine a receiver that should work for more than 10 years of life period in the harsh environment, day and night, 24 hours, all these logging. So the receiver must be very good enough for that. So even if there's a huge change in the temperature, your position data, your signal quality should not change, because with respect to the change in temperature, some cheap receivers, their output changes a lot. Okay, so you cannot have this very, very high accuracy, centimeter or millimeter level of this observation might be quite difficult. Okay, so that's all from my side. So I think it's also time. So if you have questions, so please discuss, and you can ask me or chat me. So that's all from my side. Okay, there are a few questions here.
Yeah, Dinesh, there are a few questions in chat. Could you please have a look?
Yeah. Would the LEO satellites be able to provide GNSS information? This question is not very clear to me. It can provide the correction data, so the Inmarsat and all, they are already providing the services. Okay, like some Trimble and other, they are using. I think I'm not sure about Trimble, but there are some service providers who are using this type of some correction data. I think basically they are provided by the communication satellite, but we can provide it's technically it's possible. Technically it's possible. I think there are already some service providers who provide the correction data from the LEO. But if you want to use the LEO satellite as a GPS satellite, like you want to have a constellation of the satellites of LEO satellites to give sort of a LEO GNSS, technically it's possible. And there's probably already a commercial solution available. I don't remember the name, but I think this is technically it's possible. It's possible. Yeah. Can we get better accuracy by using method than DGPS? Yes, yeah, we can do that. So that is RTK or PPP. But the requirements for RTK and PPP is that you need the carrier phase observation to have a high accuracy. Okay, DGPS is maybe 1 to 3 meters, but for RTK and PPP, you can go up to the centimeter level. But your receiver should be able to provide the raw data. We say raw data means carrier phase output from each signal. And the receiver should be able to take this type of correction data in the RTCM format. So you should have, as I mentioned, the technical spec, the receiver should have capabilities for that. And the price will go up for these capabilities and also for the receiver type. And then you need to have this base station, which is also broadcasting necessary data for RTK. So you need to have the both base station capability for RTK and also your receiver capable of that. Okay. Or if you don't have a base station, then you have to rely on the PPP solution service. Can it be possible to get a spectrum viewer from you? Sorry, no, this is not my viewer. I'm using the receiver output, so you can check from the receiver. So if you have a U-Blox F9P receiver, you can see this type of spectrum. And many other receivers like Septentrio, Jabat, Trimble, they also have it. But one thing we can do is like I do software receiver, so I write my own software to analyze the GNSS signal data. So in the software receiver, we can do this. But if you want to do this, the one I showed it, this is from this is a product from the receiver manufacturer. So I can't give you, or even if I give you the software, you can download the software from the maker side, but unless you have the receiver from the same maker, you cannot use it. Okay. Is the spoofing issue hard to solve for both civilians, and is this issue hard to solve, prevent for both civilians? Do you plan to extend your network in Africa or for? Spoofing issue is not difficult for military purpose because there's a military signal. Okay, but if you cannot use that signal, because that's a restricted signal, so outside USA probably it's not available, maybe not available for all the countries. So for the civilian signal, there's no solution at the moment, but we are developing prototypes to do some sort of anti-spoofing capabilities even for GPS. But we need to do establish a monitoring station in those areas where the service is required. So indirectly, we can do that. So whether this is Africa or Asia or any place, so we can do that. But we need to install some monitoring stations in the place where we need to provide a service. So that's possible, at least at the research and prototype level. And probably we can do something very similar with Nigeria SBAS as well. So that 1.2 for maybe research or technical studies. I think that in your previous presentation, you mentioned that multipath errors cannot be removed or even reduced. If I got it well, now you said that the choke ring antenna can reduce the multipath error. How is it done, please? I thought the only way to avoid the multipath error was to install the receiver where it is in the line of sight of the transmitting satellite. Yeah, that's what I told you that, yes, we cannot remove the multipath because it is coming all the way. So, but you can minimize to some extent by using the choke ring. Okay, maybe I don't know how much multipath it can reduce. So I myself don't have the data. So this is to some small multipath. Probably you can not a small or yeah some amount of multipath you can reduce, but not much. So it doesn't mean that you put a choke ring antenna and then you have a tall building next to you. It will not solve your problem. Okay, so this will not help. For example, we have a base station in one of our universities, and we have a choke ring antenna, but nearby we have some big trees, and we always have a problem, the multipath coming from the trees. Yeah. So this will not help totally. So it may reduce the minimize to some extent, okay? some type of multipath, but not good. It cannot remove. So in that sense, yes, it can minimize to some extent. Yeah, I should say that. About errors on RTK, considering then the antenna size is about 20 centimeter when the error achieved is of 1 to 10, that is for positioning precision, but also. Yes, so yes, so this is precision or accuracy is now two different things. So normally in the RTK, so this accuracy or the precision, whatever you call, you are getting this coordinate data with respect to the base station coordinate. Okay, so if your base station already has some error, so that error is also included in your rover unit. So this is very much related to your base station. So with respect to the base station, the position data you get, we call it the absolute position data. Okay. So that's a true position data. So we take that as a true position data. That's the accuracy, not only the precision. But if you use the PPP, we don't use the base station. We don't compute the position data with reference to the base station. So it's like a global solution. So in that sense, the accuracy or the position data that you get from the PPP solution is a sort of a global true data or the really absolute data, absolute accuracy. So in our last training, so we talk about this PPP and RTK accuracies, and which is better, and what is this relative and absolute, and so on. So in our observation, we found that PPP is a better than the RTK in terms of this absolute accuracy. L1 plus, sorry. How does the temperature of the receiver affect the accuracy or precision? It means one has to check the advance in the highest temperature at the location of their receiver for getting continuous reception. Okay, this is very highly technical question. So because the receivers, they have some analog component and they have a clock inside to generate the replica signal, because today's presentation I did not explain how a receiver works. Okay, so normally the way the receiver works is to generate the replica signal. So the receiver will generate the same signal as a GPS incoming signal, only with the code at the carrier without the navigation data, because the receiver doesn't know. So to generate this replica signal or the sample signal in the receiver, it requires a clock, some signal to generate a carrier wave. Okay. So this is generated by a clock, and this clock is very much controlled by the temperature. If there is a change in the temperature, the clock temperature, the wave you generate at every certain order of the nanosecond or few hundred nanosecond, the shape of the wave, it will be getting longer or shorter due to the background temperature. But this type of clock in the high accuracy receiver, high-end receiver, they are controlled in the oven. We call the TCXO, temperature control oscillator. So it's already inside some control environment, but still, if there is a sudden change or very high difference of the temperature, like if day and nighttime temperature variation is like 40 degrees, like in some countries, so daytime maybe plus 20 and nighttime maybe minus 20. So you have a 40 degree of temperature variation. If that happens, there's this impact on the clock temperature stability. And also there are some other circuitry and many other electrical components. And all of these components, they should work at the same temperature level. I mean that their performance must be remain the same. Okay. So, and also in the antenna or in the receiver, there's some component that's related to the analog component. So these analog components are very much sensitive to the change in temperature. So if the receiver manufacturer don't put a good quality the components in the receiver, then their performance will be different when there will be this huge difference in change in the temperature. Okay. But this will be very sensitive to the components only when there is a sudden change in the temperature, or also when there is a very large difference in the temperature in like a few hours. So the receiver manufacturer, they design, so what type of quality they want to maintain. So if you are demanding this very strict requirement, probably your cost will be quite high, because it's very difficult to maintain this level of accuracy, even when there's a big difference of change in the temperature. But in general, the temperature doesn't vary such a, extreme variation in the normal operation. Okay, if you put a receiver for 24 hours in the place in your city, so maybe change of temperature in 1 year, maybe more than 20 degrees or 30 degrees, but it changes very slowly. But this very slow change may not have effect. But if it changes rapidly and going up and down, so it may have some drastic impact on that. So this type of consideration may be required if you are doing very special applications like very high accuracy observation at the millimeter level. That's one thing for long-term observation. And another is if you want to use the receiver to monitor the quality of the satellite signal itself, because when they launch the new satellites, we need to see whether the signals coming from the satellites are well within the specifications and the standards and so on. So we need to make sure that the receiver impact, the impact of error from the receiver is minimum. So we need to have this very highly stable receiver, and temperature is one of those factors. Or you need to put the receiver in a temperature control environment so that it doesn't change much. Okay, so that's all from my side. We don't have any other questions.
Thank you, Dinesh. Okay, with that, we conclude our workshop. By now, you should have received 2 emails from Patrick, one with the link to the presentation, today's presentation, and another email with the link to the feedback questionnaire. So we would appreciate if you could spend another few minutes to complete the questionnaire. That would be great. Thank you very much, everyone, for your time and the support in participating, attending this workshop. Bye.
Yeah, thank you very much.